1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, and we stable. Let's see if it goes actually. Okay. Stable. Let's see. Something's off. Wait. Do you hear me? God of the deep. Hear me. Do you hear me? Do you hear me? Okay, I need to adjust that. Okay, I need to adjust that. Do you hear me? God, do you hear me? Do you hear me? Do you hear? Okay, I need to adjust that. Okay, I need to adjust that. Do you hear me? Okay, I need to adjust that. God, do you hear me? Okay, okay. Do you hear me? Now I should be hearable. Now I should be hearable. Now I should be hearable. Do you hear me? Okay, okay. Do you hear me? Now I should be hearable. Now I should be hearable. Now I should be hearable. Okay. We're here. Everything is captured. We can go. Enjoy our last day. I must first apologize. My computer broke and I couldn't finish this the day after or something like that. But now we're finally here. We've come to see the bold man cry, and the bold man will now show us relative velocity 1 dimensions. Let us go and let us hear what he has to say before making our judgment. Thank you.
Two objects, one and object two, moving with velocity v1, and another object v2, moving with velocity v2. Let's say they're moving on the ground. Now, I'd like to introduce the concept of relative velocity, a concept that we experience all the time in our lives, but let's see what it actually means. So v relative, I'm going to define this to be the velocity of 1 minus the velocity of 2.
Okay.
Now, because of this minus sign, that seems a little bit abstract, but one typical example where we see this all the time is for people traveling on highways. You might have two cars, one car overtaking the other car. But if you're sitting in car 1, it looks like car 2 is going quite slow. So let's just take a typical highway example. So you might have V1, and we'll give this some speed, so we'll make it 60 miles per hour, and we'll just call this a one-dimensional problem.
Why would we give
and
miles
V2,
per hour?
notice we're not speeding on the highway.
Jesus
V2 is going at 50 miles per hour. Very slow. And the relative velocity, V1 minus V2, so that's what we're calling V relative, that's 60 miles per hour minus 50 miles per hour, and that's just 10 miles per hour, and that's what people experience when one car is approaching another car. If you're in car 2, car 1 seems like it's coming at you at 10 miles per hour. This is what we mean by relative velocity. There's another important example, so that's example 1. The other important example to look at, example 2, is when two objects are moving in opposite directions. So let's just write here let's write in terms of components this time. So we have v1 x1, and we have v2, and let's make v1 x positive, so object 1 is moving in that direction. And let's write this one as v2 x. We don't have to call this initial. We'll just call it v2 x And here, v2 x is equal to minus v1 x. So its component is negative, and even though we drew an arrow in this picture, the picture is still fine because if the component is negative, it means it's moving in the opposite direction. The key arrow is the unit vector when we're writing components. And now v relative in this case is v1x I hat minus v2x I hat. That's v1x I hat minus minus, so there's another v1x I hat. So the relative speed velocity in this case has a component that's twice the speed of v1. If two objects are moving together at the same speed, the relative velocity, the way we've defined it, has twice the magnitude of either velocity. And this is an important example to consider in collisions. Now, this relative velocity concept we'll see will add a new way of thinking about elastic collisions with no external forces in one dimension.
Okay, next video. Kinetic energy in the
So we're going to return to our one-dimensional elastic collision with no external forces. So we have object 1 moving with velocity v1 initial, and object 2, maybe it's moving this way with v2 initial I hat, again on a frictionless surface, and we'll call that our initial state. And here you can imagine we're going to use a ground reference frame, so both objects are moving, and our final state has object 1. Well, we don't know, again, which way it's going. We can just say it bounced back, and object 2 also bounced back, but the goal of our problem, of course, is to determine these vectors, and by knowing the vectors, we know which way they go. Now, because energy and momentum are constant, let's write down our two equations, and I'm going to write them down again in terms of components. So we have 1/2 m1 v1 x initial squared plus 1/2 m2 v2x initial squared equals 1/2 m1 v1 x final squared plus 1/2 m2 v2x final squared. Now, we're going to do some algebraic manipulations here. So the first thing I'm going to do is just eliminate these halves because it's not necessary, and I don't want to rewrite this equation. And this is our fact that our energy is constant. And now our condition that momentum is constant, we'll write this now. I'm going to leave a little space here intentionally. And our condition that momentum is constant is m1 vx initial plus m2 v2x initial equals m1 v1x final plus m2 v2x final. Now, this energy equation can be factored in by bringing all the m1 terms to one side and the m2 terms to the other side. So when I write that on the little room, I have m1 v1x initial squared minus v1x final squared. And that's equal to m2 v2x final squared minus v2x initial squared. So I just brought those terms over the other side. Now, likewise, I'll do the same thing down here. I have m1 v1x initial minus v1x final. And that's equal to m2 v2x final minus v2x initial. Now, here comes the algebraic trick in which I'm going to linearize these systems. This is a squared minus b squared, which factors into a plus b times a minus b. So let's give ourselves a little room. m1 v1x initial plus, let's put the minus sign first, minus v1x final times v1x initial plus v1x final. Factor that term. We have the same factoring on the other side. So it's just identical v2x final minus v2x initial times v2x final plus v2x initial. Now, let's call this equation 1a, and our momentum factored as 2a. Now, if you notice, the momentum piece is appearing exactly there and exactly here. So when I divide 1a by 2a, and I'll just symbolically represent that, then these two pieces cancel, and that leads to just this term equal to that term. And the significance, as you'll see when I write it out, 1x final equals v2x final plus v2x initial. I've eliminated the square terms, linearized the system. Now, I still want to write this equation in another way. Another important point to notice is that this equation is independent of mass. Now, what I want to do is write this in terms of those concepts of relative velocity we had. Remember, just to motivate this, the relative, by definition, was v1 minus v2. So let's write this in terms of the initial and the final. So in order to do that, we have to bring this initial term over to here and this final term over to there. And so this equation, which we'll give it a number 3, and now we'll modify that by calling it 3a. We have v1x initial minus v2x initial. Now notice the sign. I'm going to want to keep the order of 1 and 2, so I have to put a minus sign, v1x final minus v2x final. And when written this way, this is the initial component of the relative velocity, and in there is the final component of relative velocity. So by combining these two equations, I have this remarkable result that v relative initial is minus v relative final. And this condition is a very powerful tool for simply analyzing one-dimensional elastic and elastic collisions. I like to even give this a name. I like to call it the energy momentum equation. Now, there's a lot of significant things about this, so let's just think about it for a moment. We have that v relative initial in magnitude is equal to v relative final. And so right away, this gives us some insight into any collision. We can see whether a collision, if we know what the relative initial velocity is, we know that the final relative velocity has the same magnitude, but simply switches direction. And that's a powerful tool in which to analyze collisions without doing a lot of algebra. We now would like to apply our energy momentum rule and momentum to analyze a one-dimensional elastic collision with no external forces. Let's remind ourselves, we'll call it the energy momentum equation. Said that v relative initial was equal to v relative final. So we have v1 x initial minus v2 x initial. That's the initial relative, the x component of initial relative velocity is equal to the final x component of the relative velocity. And that was our energy momentum law. Now the momentum condition, that is constant, was our equation v1 x initial plus m2 v2 x initial equals m1 v1 x final plus m2 v2 x final. Now, let's see how this linear system is much, much easier to solve. Let's look at the same problem that we solved before, where m2 was equal to 2m1. And also, we were in the laboratory frame, so v2x initial is 0. And that tells us that the initial velocity, relative velocity, is simply the velocity of object 1. So let's just write our two equations down again and see how much simpler our system is. v1x initial is minus v1x final plus v2x final. So we have minus plus, and our momentum condition, remember v2x initial is 0, the m1, m1, m2 will be 2m1, so we can cancel our m1s, and we get v1x initial equals v1x final, and m2 is twice m1, so there's a factor plus 2 v2x final. Now, I want to solve for our target variable. I look at these two equations. I can see almost immediately that if I add these two equations, v1x initial will cancel, and I get very simply by adding, we get 2 v1x initial, and this is 3 v2x final, or v2x final is 2/3 v1x initial. And let's just call this equation 1 and 2, so we added. And now to find v1x final, we, let's see what we'll do there. So we can do this a variety of different ways. I think the simplest thing here to do, we could eliminate v2x final by multiplying through by -2, or we can simply substitute in v2x final right here.
v1x final is equal to 1.
We get, so let's do that. Let's substitute that in right there, and we get v1x initial equals v1x final plus 2 times 2/3 v1x initial. When we bring that over to the other side, 1 minus 4/3 is minus 1/3 v1x initial equals v1x final.
Yeah.
And at the cost of introducing a new concept, we found the algebra much, much simpler to solve in this problem. And we can just double check our result that the initial velocity, relative velocity, was simply vx1, and the final relative velocity, v relative final, is minus v1x final, minus, let's see, the v final relative velocity is v1x final, v2x final I hat, and when we put that in, we have minus 1/3 v1x initial, minus 2/3 v1x initial I hat, and we have minus v1x initial I hat, which is minus v relative initial. And so we see that the relative velocity simply changed direction. This approach is much, much easier, and keep in mind that the energy momentum and the momentum laws are just rewriting our two fundamental constants of motion, kinetic energy and momentum.
Let's consider a gravitational slingshot. What is that? Well, once in a while, people like to send spacecrafts out into the solar system, particularly the outer solar system, to explore what's going on there. And because we can't on Earth give enough speed to these little spacecrafts, we need the big planets around us to help us a little. And so we can consider a large planet like Jupiter or Saturn. Here we have Saturn. And if we have a little spacecraft and we make it fly by close, then what actually happens is it will, due to the gravitational attraction of Saturn, acquire a kick in velocity, and that is a gravitational slingshot. So let's look at that. So our little spacecraft comes in with an initial velocity, and Saturn, of course, also has a velocity. And once it has passed, our little spacecraft will have a final velocity. And in order to calculate what this final velocity is going to be, what the increase in speed is going to be, we need the concept of relative velocity. And for that, we need to first consider some initial state. So we have the relative velocity initially, and that is the difference between those two velocities, between the spacecraft and Saturn. And what becomes very important here is that we look at the coordinate system and keep that in mind, otherwise we're going to get a few sign errors. So the initial velocity of the spacecraft goes in the I hat direction, and the velocity, the relative velocity is of course a difference, so minus the velocity of Saturn, but that one goes in the minus I hat direction. And then we have the final state, so v final relative, and here we have the final velocity of the spacecraft now going in the minus I hat direction, minus the velocity of Saturn, that also goes in the minus I hat direction. Now there's one thing that we need to consider, which is this velocity of Saturn. This one actually is, of course, here the initial velocity of Saturn, and this one is the final one. But because the mass of Saturn is so much larger than the mass of the spacecraft, we can actually set the initial velocity of Saturn to the final velocity of Saturn. So we can turn this, we can take this away here again and just consider one velocity of Saturn. Okay, good. There's one more thing that we need in order to solve this, because we need to know how the relative velocities are actually related. And the energy momentum law helps us there, because that gives us that the initial relative velocity equals minus the final relative velocity. Okay, so we can plug that in now. What do we have here for the initial velocity? We have vi minus twice gives us a plus the Saturn velocity, and that equals minus minus gives us a plus the final velocity of the spacecraft. And then we have 3 minuses here, so that gives us a minus the Saturn velocity. And we know from the problem that the initial velocity here of the spacecraft was actually given at 3 Saturn velocities. So we can tally this up now. We have 3. We have 3 plus 1 is 4, and we'll put this over on the other side. That gives us 5. 5 Saturn velocities equals our final velocity. So that's quite a good gain, I would say, and it nicely illustrates why big planets like Jupiter and Saturn are really, really helpful for the exploration of the solar system. And that is actually how the New Horizons mission made it out to Pluto, all the way out there.
Mm-hmm.
We would now like to look at two-dimensional collisions. And what we like to look at is in the laboratory frame, so I'll call that the lab frame, in which we have a target particle, which I'm going to call 2, and an incoming particle 1, which is coming in with some initial velocity. After the collision, let's imagine that the target particle is going out at a certain direction, so we'll call that 2. And the target particle has a velocity v2 final, and the initial particle that's going in this direction, we'll call that 1, and that is its outcoming velocity. Now, in this collision, we want to ask ourselves first, what quantities are constants of the motion? Well, let's assume no external forces, therefore momentum is constant, and we can write our momentum equation as m1 v1 initial equals m1 v1 final plus m2 v2 final. Now, recall that momentum is a vector, and so what we have here are the unknowns here are our 2 outcoming vectors, v1 final and v2 final, and a vector in 2 dimensions has 2 quantities. We can write that as components, or we can write it in terms of magnitudes and directions. Now, experimentally, we often will measure the directions of the outcoming particles, which I will now indicate by theta2 final and theta1 final. And so when we write our two momentum equations, we can either write it as components, or we can write it in terms of magnitudes and directions and do vector decomposition. Now, because we measure the outcoming directions, we're going to choose to do magnitudes and directions. So let's indicate a little notation. We'll say that the magnitude of V1 initial is V1I, and the magnitude of V2 final is V2 final, and the magnitude of V1 final is V1 final. And so now, when we look at our two momentum conditions, we now also have to introduce unit vectors for directions. So let's call I hat that way and j hat in this direction. And in our I hat direction, we have only the incoming momentum, and we can write that as m1 v1 initial. It's positive because we've chosen the forward direction as our I hat direction. Now, in terms of the outgoing momentum in the I hat direction, we have to do vector decomposition of both of these vectors, and they both have positive components. So we have m1 v1 final, that's the magnitude, cosine theta 1 final, plus positive sign because they're both in the positive direction, v2 final magnitude times, we need that little m2, v2 final, cosine theta 2 final. And that is our I hat direction. Now the j hat direction, remember, we have to be careful because we're taking positive j hat up, so our particle 2 has a positive component in the j direction, and our particle 1 has a negative component in the j direction. The incoming momentum, there's no momentum in the j direction, so we have a 0, and that's equal to positive m2 v2 final, and that's a sine theta 2 final. Now here's where we have to be careful because this one is negative, component is in the negative j hat direction, and we have m1 v1 final sine theta 1 final. And these two represent our momentum equations. Now we also have to think, let's think about energy. Again, we have to know something about this collision, and our assumption will be that this particular collision is elastic. And that means the initial kinetic energy is equal to the final kinetic energy. Energy is a scalar. We've been describing our incoming velocity vectors in terms of magnitudes, so we can write our elastic energy condition as the incoming kinetic energy squared, that's the kinetic energy incoming, is equal to 1/2 m1 v1 final squared plus 1/2 m2 v2 final squared. And that is our kinetic energy condition. Let's label this equation 1 and equation 2. Now, it's very important to realize which quantities are given and which we need to solve for. So in this problem, because the two outcoming velocities are unknowns, we have 4 unknowns. Those unknowns can be written in terms of the two velocity final, and the other one, the 2 final. Those are our vector quantities, but recall in terms of the scalar magnitudes, we have that v1 final, and I'll just write the other ones down, v2 final, and the two outgoing directions, theta 1 final and theta 2 final. So these are our 4 unknown quantities, but you can see we only have 3 equations. And therefore, if we want to determine the outcomes, we need to measure 1 additional quantity. Now, that's very useful when doing problem solving, because when you start to read a problem and you look at what's being measured, you can right away determine which of the 4 quantities has been given. You may be given an outgoing magnitude or of the velocity, or you may be given one of these scattering angles. And so that's how we approach two-dimensional elastic collision. Of course, there's algebra now to solve for any particular quantity that you're interested in, provided you have this extra additional information.
Yes.
We'd like to examine the motion of 2 particles. Here's particle 1, and here's particle 2. And each particle can have some motion. In between them is the center of mass. And what we'd like to do is figure out how to describe the motion of each of these particles with respect to the center of mass. So let's choose some coordinate system. Origin down here. Here's our particle r1, here's our particle r2, and here is our center of mass. Now, in the reference frame of the center of mass, we have position vector r1 prime, and we have position vector r2 prime. And what we'd like to do is find expressions for r1 prime and r2 prime in terms of the positions of r1 and r2. Now, recall that the position of the center of mass for this two-body problem is given by m1 r1 plus m2 r2 divided by the total mass. And here we use the vector triangle that r1 prime equals r1 minus r center of mass. Now remember, this vector is equal to this vector minus that vector. Sometimes people like to say the vector r1 is equal to r plus r prime, and that's how we get that relationship. Now we can use our result here, that r1 prime is r1 minus m1 r1 plus m2 r2 divided by m1 plus m2. And when we combine terms, let's just do this so you can see it. r1 minus m1 r1 plus m2 r2 divided by the total mass. We now have the m1 r1 terms canceled, and we have a common m2 over m1 plus m2 times r1 minus r2. Now r1 minus r2 is a vector that goes from here's r1, here's r2. So the vector r1 minus r2 is the relative position of vector 1 with respect to 2. And let's give that a special name. We'll call that r12, the relative position vector. So we have m2 over m1 plus m2 r12 is r1 prime. Now, you can easily see that if you interchange the indices 1 and 2, the only thing that changes here is a sign. And if we interchange 1 and 2, and this is an exercise that you can do, then r2 prime is minus m1. I'm interchanging the indices. The minus sign came from the interchange of 1 and 2. And so we get m1 over m1 plus m2 with a minus sign r12. Now, what is the significance of this result? If you know the position of r1 and r2, you know the relative velocity. If you have information about this relative position, if you know the relative position vector, then you can separately get the locations of the two objects in the center of mass frame. Now, this quantity in here will appear often, and I'd like to introduce a new quantity called the reduced mass. And that reduced mass, mu, is the product of m1, m2 over m1 plus m2. It's a simple exercise to see that 1 over mu is 1 over m1 plus 1 over m2, and we'll encounter that a little bit later. Then I can write both of these vectors, and this is our conclusion, that r1 prime is the reduced mass. Notice we have an m2 here, so we have to divide by m1 times the vector r12, and r2 prime is minus the reduced mass. Again, we now have to divide by m2, and you see this nice symmetry of m1 and 1, 2 and 2, r12, and that's our key result. When we analyzed a one-dimensional elastic collision in any frame, and we had a velocity v1 initial and v2 initial, that we saw that we could reduce, this is a one-dimensional elastic collision, we could reduce we always have the energy condition and momentum condition, but when we combine the energy and momentum together, we found the following idea, that the relative velocity, v12, which we call the relative velocity initial, was just equal to the final relative velocity. The statement there was that v1 initial minus v2 initial is equal to minus v1 final minus v2 final, and we called this the energy momentum relation for our classical mechanics, and then we could combine that with our conservation of energy law, conservation of momentum, and we've got a linear system of equations that is much easier to solve than the quadratic system. Now what I'd like to show is that this concept of relative velocity, that the v12 relative velocity is independent of the choice of reference frame. And so if we want to analyze a collision in any other reference frame, then we always can keep this result. So now let's look at that. So again, let's imagine that we have two particles, where we have particle 1 and particle 2. We have some origin, r1 and r2. And now we want to choose another reference frame. So suppose that we pick a second reference frame, which has maybe some origin over here, and we have the vectors r1 prime and r2 prime, and the relative vector from the center of one reference frame to the center of the other reference frame. So what we have are the two conditions that r1 is equal to capital R plus r1 prime, r1 is capital R plus r1 prime, r2 is capital R plus r2 prime. And now if we subtract these two equations, we have r1 minus r2 equals r1 prime minus r2 prime. And this shows us that the relative position vectors, and let's draw that R, this one, from 2 to 1. And even in our diagram, we can see that the vector from 2 to 1 does not depend on the choice of reference frame. And even more importantly, when we differentiate, we get that v1 minus v2 is equal to v1 prime minus v2 prime, and that becomes our statement that the relative velocity vector is independent of the choice of reference frame.
It is.
Let's examine the velocities of an object in the center of mass reference frame. So we have object 1 and object 2, and we have Cm, and we have r1 prime, and we have r2 prime. And recall that we found that the position vector r1 prime was equal to the reduced mass over mu m1 times the relative position vector r12. I'll draw that up here, r12 from 2 to 1, and just to remind you, r1 minus r2. And likewise, the position vector r2 prime is minus mu m2 over r12. Well, now we can differentiate the positions in the center of mass frame, and we find that v1, which is, of course, the derivative of the position, is just mu over m1 v12, and v2 prime is equal to mu over m2 with a minus sign v12. Now, the significance of this result is that the velocity of the object in the center of mass frame is equal to some constant times the relative velocity. Likewise, velocity v2 prime in the center of mass frame is also proportional to a constant, and it's in minus the relative velocities. So the significance of this result is that when we look at an elastic one-dimensional collision, we already have the result that the relative velocities, v12 initial, is minus the final relative velocity. And we also know from what we saw that the relative velocity is independent of the reference frame. So this condition about relative velocity is true in any reference frame, and in particular, it's true in the center of mass frame. So what that shows us is that this condition, the statement, is that the magnitude of the relative velocity is constant. And the conclusion is because in the center of mass frame, v1 prime is proportional to the relative velocity. That tells us that in the center of mass reference frame, that the initial velocity of object 1 in the center of mass frame is equal to the final velocity of object 1. So the quantity, the speed of objects 1 and objects 2 in an elastic collision in the center of mass reference frame do not change magnitude. We can call this quantity v1 prime, and likewise v prime 2 initial is equal to v2 final prime, v2 prime, and this will make our analysis of collisions in the center of mass reference frame very easy. Two objects, when they're colliding in the center of mass reference frame, their speeds do not change. Only the direction of their velocities change. Let's consider a collision in a lab frame in which one particle is coming in and the other particle is at rest. So here's particle 2, v2 initial is 0, and we could say that m2 is twice m1. And this is our lab frame. And now let's consider the same collision in the center of mass frame. And in that reference frame, we have particle 1 moving with velocity v1 prime initial, and particle 2 moving with velocity v2 initial prime. Now, the way we're going to analyze this problem is that we know the speeds in the center of mass frame relative to the lab frame. So we actually know these initial speeds, and we'll write that result down in a moment. Because we know the initial speeds, we also know that v1 final in the center of mass frame is just minus the initial velocity. That's the beauty of the center of mass frame. The velocities just change direction, they don't change magnitude. Because we know this, we can get v1 final, and then it's just a simple exercise to go back to the lab frame to calculate the quantity, the velocity of object 1 in the lab frame. So that would be our sequence of ideas. And the key fact that we know is that v1 prime is equal, initially, to the reduced mass divided by m1 times v12, where v12 initial is just equal to v1 initial minus 0, so that's v1 initial. And the ratio, mu over m1, it's very simple to calculate that. That's just m2 over m1 plus m2. For our case, that's 2/3. And so from our result, we now have very simply that v1 final prime is minus v1 initial prime. So it's minus 2/3 v1 initial. And that's a very straightforward calculation. We can do exactly the same thing with v2 final prime. v2 final prime is minus v2 initial prime. And v2 initial prime is equal to minus mu over m2 times v1 2 initial. This ratio, instead of being 2/3, it's a simple exercise. It will be m1 over m1 plus m2 is 1/3 v1 initial. And so we have solved for the final velocities in the center of mass reference frame. Now let's just double check our results. We have v2 final is minus v2 initial, so that's minus, but there's another minus sign here, so we have two minus signs, so that's a plus, and that's why we have the plus 1/3 v1 initial. And finally, if we want to ask the question, what are the velocities in the lab frame? It's now a very simple exercise to do reference frame change. We do need to know what the center of mass is. That's v1 v initial over m1 plus m2, because remember that v2 initial is 0, so that's another factor, v1 initial. And now, for conclusion, we have that the final velocity in the lab frame is equal to the velocity in the center of mass frame plus v center of mass, and we just collect our results, minus 2/3 v1 initial plus 1/3 v1 initial, so that's minus 1/3 v1 initial, the outgoing velocity of particle 1 in the lab frame, and the outgoing velocity of particle 2 in the lab frame. Again, we have 1/3 v1 initial plus another 1/3 v1 initial is equal to 2/3 v1 initial. So we were able to solve this problem by switching reference frame using our basic fact in the center of mass frame that the speeds remain the same, but the direction changes, and able to solve this problem without any of the traditional ways of applying the energy-momentum relationship in kinetic energy or having quadratic equations.
Impressive.
Let's compare kinetic energies in a two-particle one-dimensional collision in different reference frames. So we could have one reference frame in which particle 1 is coming in and particle 2 is moving like that. And in particular, so we can call this the ground frame. And now let's consider the center of mass frame. And in the center of mass frame, let's remind you that when we have two different reference frames, the velocity, we'll call this the ground frame g, in the ground frame, is equal to the velocity of the object. We'll actually write it this way, just unprimed, v1. The velocity in the center of mass frame, so this is the velocity in the CM frame, plus the relative velocities between the frames, and that's why that's the velocity of the center of mass. So this was our rule for describing how velocities change in different reference frames, and so we can draw the picture in the center of mass frame, v1 initial prime and v2 initial prime. Now let's compare kinetic energies in these different frames. So we know that the kinetic energy in the center of mass frame is just 1/2 m1 v1 initial squared prime, put the prime there, plus 1/2 2 initial prime squared, kinetic energy in the center of mass frame. How do we calculate the kinetic energy in the lab frame? Well, that's a little bit more complicated, and we'll need a little algebra to start that. So let's put kinetic energy in the ground frame. We know is 1/2 m1 v1 initial squared plus 1/2 m2 v2 initial squared. Now what I have to do is use the law, the velocity relationship, and this is going to take a little bit of algebra. We have m1. I'll write v1 prime plus vcm, and remember that any quantity squared is the dot product, v dot v. So I'm going to dot this with itself, v1 initial prime plus v center of mass. And I have a second term which looks identical to this first term. I'll write it all the way down here, 1/2 m2 v2 initial prime plus vcm, vector dot scalar dot product of v2 initial prime plus vcm. Now, when you take a dot product, remember there's four terms here. There's v1 prime dot v1 prime, which is just v1 prime squared. There's v center of mass dot v center of mass, so that's v center of mass squared. And then there's the cross term. And because they're identical, there's a factor of 2, and it will be repeated below. So the kinetic energy in the ground frame is 1/2 m1. So we'll take v1I prime dotted with itself. That's v1I prime squared. We have the cross term, which is a factor of 2, which will cancel this. So the cross term is m1, that cancels the factor of 2, v1I prime dot vcm, plus the vcm with itself. So that's 1/2 m1 vcm squared. Now I have exactly the same thing on the next one. So we'll write that down, 1/2 v2I prime squared plus m2 v2I prime dot vcm. That's the same in both, plus 1/2 m2 vcm squared. Now, let's look carefully what we have. We have 1/2 m1 v1 prime squared. This is an m2. 1/2 m2 v2I prime squared. So we have 1/2 m1 v1I prime squared plus 1/2 m2 v2I prime squared. And you're already noticing that's the kinetic energy in the center of mass frame. We have the total mass, 1/2 m1 plus m2 vcm squared. I can just put a little check to show which terms I've done so far. And now here's the interesting one. We have m1 v1I prime plus m2 v2I prime dot vcm. That represents this term and this term added together. But recall that the center of mass reference frame is defined by the condition that the total momentum in that frame is 0. So this term is 0. And thus we get that the kinetic energy in the ground frame is equal to the kinetic energy in the center of mass frame plus 1/2 m1 plus m2 times vcm squared. And that's how kinetic energy is in different reference frames. And the next thing we'll look at is how that changes when we have a collision. Let's calculate the kinetic energy in the center of mass frame of two objects that are colliding. I'm going to use prime for the center of mass frame velocity. So we have v1 prime and we have v2 prime. And recall two things. that when we calculated v1 prime in the center of mass frame, we found that this was equal to the reduced mass divided by m1 times the relative velocities of the two objects, v1 prime minus v2 prime. Now, in the center of mass frame, this quantity is reference frame independent, and so we can just write that as v12. It's the relative velocity is reference frame independent. So we also knew that v2 prime was equal to minus mu over m2 v12. So now let's calculate the kinetic energy in the center of mass frame. So kcm is 1/2 m1 v1 prime squared plus 1/2 m2 v2 prime squared. Now let's use our results in terms of relative velocity. So we have 1/2 m1 mu over m1 times v12 squared, because we're squaring that, plus 1/2 m2. Mu, the minus sign doesn't matter anymore because we're squaring it. v2 squared, I could put that in there, it wouldn't matter. And now what we have is we have a half. One of the m1's cancels, so we have a mu squared over m1 v12 squared plus 1/2 another mu squared over m2 times v12 squared. So I pull out the common terms, mu squared, v12 squared. I have 1 over m1 plus 1 over m2. But recall that the reduced mass was precisely 1 over m1 plus 1 over m2, and so I get 1/2 mu times v12 squared is the kinetic energy in the center of mass frame. So what that means is a way of thinking, if this were just a simple reduced mass problem with a relative speed of v12 squared, I can write down the kinetic energy, but that's the kinetic energy in the center of mass frame. And therefore, the change in kinetic energy is, in a collision, is just 1/2 v12 initial final square minus, and it's the same mu, so we'll just put parentheses, minus v12 initial square. And if the collision is elastic, remember our elastic collision showed that v12 initial was minus v12 final. So an elastic collision satisfies that condition, and you can see directly that delta kcm is 0 in that case. And a completely inelastic collision has the two objects moving together at the end, so v12 final is 0, so completely inelastic is the condition that v12 final is 0, because the objects stick together. And then we have a very simple result for the change in kinetic energy for completely inelastic collision. It's only negative 1/2 mu v12 initial quantity squared. Now, when we did these calculations, we saw that the kinetic energy in the ground frame was equal to the kinetic energy in the center of mass frame plus a constant term, m1 plus m2 times vcm squared. And this is a constant, whether you're in the initial or the final picture. So if we look at the change in kinetic energy in the ground frame, that's equal to the change in kinetic energy in the center of mass frame, but this term is a constant, so there's no change in that term. And so we have a crucial result that the change in kinetic energy in the ground frame is equal to the change in kinetic energy in the center of mass frame. Now let's look at an example of a collision that's completely inelastic. So we have object 1, and it's coming in with v1 initial, and object 2, let's make it at rest. And afterwards, object 1 and 2 stick together, and they go off with v final. So here's a collision in the inelastic frame. Now in the center of mass frame, the two objects, so here's our lab or ground frame. I can call it the lab frame because that one's at rest. And this is the CM frame. And there we have v1 prime and v2 prime. They're both moving. And now, in the center of mass frame, they're at rest at the end of the collision. So in this collision, we can analyze it. And now what I want to show is that the change in kinetic energy, recall from our previous calculation, that the kinetic energy in the center of mass frame was equal to 1/2 mu times the relative velocity squared. So remember, v12 was equal to v1 minus v2. And so the change in kinetic energy in the center of mass frame is the final kinetic energy is 0 minus 1/2 the kinetic energy in the initial state. And what is this quantity initial? Well, this was a reference frame independent concept. So we can just look at the lab frame and write this as v1 initial I hat, where that's I hat because this object is at rest. And so right away, we have that the change in kinetic energy is minus 1/2. Now remember, mu was m1 m2 over m1 plus m2 times v1 initial squared. And that's the same change in kinetic energy as the ground frame. So by using our result here and our result there, we were able to very quickly assess how much kinetic energy is lost in this inelastic collision. And where does that kinetic energy go? It can go to a variety of places. Deformation of objects. It can go into sound. It can go into thermal energy that gets re-radiated, that is transmitted into the environment through, diffuses into the environment. However, that's how much is changed.
Up until now, we have been studying the motion of point-like objects. In this module, we are going to consider the motion of extended objects, specifically objects that are rigid bodies. By rigid, we mean that the distance between any 2 points on the object always stays the same. In other words, the shape of a rigid body does not change or deform. There is a useful relation known as Schall's theorem that states that the general, arbitrarily complicated displacement of a rigid body can be broken up into 2 parts. First, the translational motion of its center of mass, and second, a pure rotation of the object about its center of mass. We already know how to analyze the center of mass translational motion through our study of point-like objects. This week, we will consider the rotational motion of rigid bodies, once again distinguishing between kinematics, the geometric description of the motion, and dynamics, the underlying cause of changes in the rotational motion. On a microscopic level, we can think of an extended rigid body as made up of a very large number of small point-like pieces all attached together. For rotation about a fixed axis through the center of mass, each little piece will move in a circle about the rotational axis. The radius of the circle will vary depending upon where in the object that particular piece sits. However, because all of these small pieces are moving collectively as part of a single rigid body, they will all have the same angular velocity and angular acceleration at any given instant. This gives us a way to specify the kinematics or geometrical description of rotational motion using the vector quantities of angular velocity and angular acceleration. We will also consider the dynamics of rotational motion. We will see that an applied external force is able to change the rotational motion of a rigid body depending upon exactly where on the body the force is applied. This leads directly to the concept of torque, a vector quantity that represents a sort of rotational force. Finally, we will see that we can link the kinematics and dynamics of rotational motion through a rotational equation of motion, analogous to the role that Newton's second law plays for translational motion. This relation states that the angular acceleration is proportional to the applied torque, and also depends upon how the mass of the object is distributed.
So far in the course, we've been studying the motion of collections of particles. We would now like to consider rigid bodies. Now, rigid bodies can be translated in space, as I move it like this, or we can rotate this rigid body about some point. I can rotate it about the endpoint. I can rotate it about a point which we call the center of mass. So I can rotate it about the center of mass. I can take the rigid body, and I can rotate it about the center of mass, and also translate it in space. So there's many types of motions that we can do with rigid bodies. Sometimes the motions are quite complicated. If I spin it like that, it is a very more complicated motion. You can see that it's rotating about this axis. So what we'd like to do now is analyze how to think about the motion of rigid bodies. And what we'd like to do is idealize our rigid body. So let's just draw, even though we look at a rod here, let's just draw some extended idealized rigid body. And let's identify 2 points in that rigid body, the J point and the K point. And we'll think of our rigid body as a bunch of point-like particles, Mj and Mk. And the important thing that defines a rigid body is the condition that the distance, and we'll draw this a vector from the K particle to the J particle. So we'll draw that as R, J, K. And actually, I would like to write it from the K particle to the J particle, R, K, J. And our condition is that the magnitude of this vector, which I'll denote as RKJ, is constant for all points, J and K. Now, what does that mean? That means the distance between any 2 points in the rigid body stays fixed, no matter how the rigid body is moving. And no matter what 2 points I choose, the distance between any 2 points is fixed. So we'll rewrite this as the distance between any 2 points is fixed. So that doesn't change. And that's what we call the rigid body condition. So we're now beginning to make our complete study of rigid body motions about fixed axes. Let's consider something like a bicycle wheel. Here's the center of mass of the wheel, and our bicycle wheel is the center of mass has some velocity. And here's ground, and we're going to call this, the reference frame is the ground frame. Now, if the bicycle wheel is rolling, then there'll be some type of rotational motion of the wheel. So you can imagine point on the rim is rotating. And so what we have here is a angular velocity of this bicycle, which we'll write like this, our vector omega, and we'll use our right-hand rule to establish that direction for omega. And now, in this reference frame, we have translational motion of the center of mass, and we have rotational motion around the center of mass. If we go to the center of mass reference frame, so if you want to just a little cartoon to show that, here's your observer, and your observer is moving with BCM. And so in that frame, the center of mass is at rest, and the only thing we have is rotation about the center of mass. And so in this picture, our motivation will be that the total external force causes the center of mass to accelerate, and that's how we can figure out the center of mass motion. And in this picture, we no longer have to consider translational motion, and what we'll study and learn to analyze is just pure rotation about the center of mass. So torque will produce angular acceleration. We can talk about the rotational energy about the center of mass. And so we'll begin our analysis of rotational motion, of translation and rotation, by focusing our interest in the center of mass frame, so we've just isolated the rotational motion. Suppose we have a rigid body, and it's rotating about a fixed axis, and we know that the angular acceleration alpha is given. Now, it may be a function of time, and we'd like to find from this the angular velocity and how much angle has rotated in some time interval. So the first thing we have to do is choose a point in the rigid body and introduce a coordinate system. Here we have our angle theta, and at this point we have our r hat and our theta hat direction. And recall that by the right-hand rule, the k hat is going out of the plane of the figure. And so we have our coordinate system. And we wrote alpha as the second derivative of theta with respect to time k hat. Now our goal is to find omega, which we'll write as the first derivative of d theta dt k hat, and also to find theta as a function of time. Now recall that our notation was that alpha z was d omega z dt equals d squared theta dt squared, and in this notation omega z was equal to d theta dt. Now what we're going to do is we're going to integrate alpha, just like we did in simple circular motion kinematics for point-like objects. And so what we have here is that for some time interval, omega z at time t minus omega z 0 is the integral of t prime equals 0 to t of alpha z, which is our component of the angular acceleration. We have an integration variable dt prime. And recall that that implies that omega zt can have some initial value at time t equals 0 plus this integral relationship, which is what we want to figure out by direct integration. Now this only works when alpha z is some function of time. In order to get the angle theta of t, we integrate again, where we have theta of t 0 is the integral from t prime equals 0 to t prime equals t of this function, omega z. Again, we have some integration variable t prime dt prime, and so we see that theta of t can have some initial value plus this integral relationship t prime equals t of omega z t prime dt prime. And this is how we can figure out how the point p has a component of angular velocity and what angle the point p sweeps out in somewhat time interval t. We are now considering the motion of a rigid body, and we'd like to talk about kinetic energy of rotation and properties of that rigid body. Let's consider a rigid body. And let's say that our rigid body is rotating about an axis passing through a point S. If we look overhead at our rigid body, then what we're going to do is introduce a coordinate system. So this is our overhead view. And suppose that we have a small element of our rigid body here, which I'm going to write as delta mj, and that's a distance rj from the center. Our rigid body has an angle theta, and what we'd like to do is describe a coordinate system r hat, theta hat, and k hat, pointing like that. Now, with this rigid body that's rotating, we describe the angular velocity as the rate that the angle is changing with respect to k hat. And so we can draw the vector omega, and this establishes our coordinate system for our rigid body and a small element of mass delta mj. Now, what we'd like to consider is, what does this mass element do? Imagine that it's over there. Because every point in the rigid body has the same angular velocity, this object is going in a circle with angular velocity omega. Recall that omega is perpendicular to the plane of motion, but the object itself has a velocity, which I'm going to write vj, and that velocity vector, vj, is in the tangential direction, and it's related to the z component of our angular velocity by the following relationship. It's how far we are from the center point S times the z component of the angular velocity, and it's pointing in the tangential direction. So remember that omega z is equal to d theta dt. And this describes our coordinate system for the rigid body. Now what we'd like to discuss is the kinetic energy. And the way we're going to consider kinetic energy is we're going to sum up the rotational kinetic energy of every single mass element. So we begin by writing kj rotational, and we know that that is just 1/2 times the mass element times the velocity of that element squared. Now we can use our relationship for the tangential velocity element related to the angular velocity, and we have 1/2 delta mj rj squared times omega z squared. Now keep in mind that omega z is the same for every single mass element, but the distance to the mass element are all different by rj. So the total rotational kinetic energy is the sum over j from 1 to n of, let's put the half outside, times delta mj rj squared. Now again, recall that every element has the same omega z, so I can write parentheses omega z squared. And that's our rotational kinetic energy. Now what we want to do now is look at the limit as our delta mj becomes very small because we have a continuous body, and we'll write a definition, which is going to be the moment of inertia passing through this point S, about the axis passing through S, is equal to the limit as delta mj goes to 0, or n goes to infinity, of this sum, delta mj rj squared, j goes from 1 to n. Now, because this is a limit for the continuous body, we'll define it as the integral over the body of a small mass element dm that's a distance r squared. Now here, what is the meaning of the r? Well, for our continuous body here, if we call this dm, and we define the distance from S to the body r, and now I'm going to just put a little notation in here. It's the distance from S, the axis we're calculating, about to where the body is dm, so I'll write S dm. And this is what we call the moment of inertia of a continuous body. Now, again, what's very important to realize is a moment about a particular axis. So this is about an axis passing perpendicular to the plane of rotation and through S, the point S. So it's an axis that's passing perpendicular to the plane of rotation, passing through the point S. And this is what we call the moment of inertia of a body. Now we'll see that the moment can be expressed in terms of our other physical quantities. As the course develops, you'll see 2 or 3 more fundamental relations for moment of inertia. But what we'd like to do now is summarize our results, that the kinetic energy of rotation is 1/2 for rotation about this axis. I'm just going to indicate passing through S of is times omega z squared. Now keep in mind, because omega z is a component, it can be positive, 0, or negative, but the square is always a positive definite quantity, and that's our kinetic energy of rotation. Let's contrast that with our translational kinetic energy, and we remember there that was 1/2 times the total mass of the object times v squared cm, where we're looking at all of the object at the center of mass, and this is the total mass of the object.
Understood, Captain.
I would now like to show you how to calculate the moment of inertia of a typical continuous body. Let's consider a rigid rod, very thin, and what we want to do is calculate the moment of inertia of this body about the center of mass. Let's say the body is of length L, and it has total mass M. Now recall that the moment of inertia about the center of mass we defined as an integral of dm r squared integrated over the body. Now our challenge today is to understand exactly what all these terms are in this expression. What is dm, what is r, and what do we mean by an integral over the body? So now let's do a stepwise interpretation of each term. The crucial thing is to introduce coordinate systems. So let's choose a coordinate system, and let's put the origin at the center of mass. Now, the most important thing is that we're going to do an integral, so we need to introduce the integration variable, and that's the hardest part of setting up integrals. So what we want to do is arbitrarily choose an element dm. So there's our element dm, and here's our integration variable. It's a distance x from the origin. So that's the integration variable. Now, there's 2 things when we set up the integral. R is equal to that integration variable. R is abstract in this expression, but in this concrete realization, it is the integration variable. The second place the integration variable shows up is in dm. dm is the mass in this small element, but if we want to express that in terms of our integration variable, we have to express it in terms of the differential length dx. So dm, mass, is equal to the total mass per unit length, we're assuming the rod is uniform, times the length dx of our small piece. And now we've set up the 2 pieces that are crucial, and all we have to think about now is, what does an integral mean? Well, an integral means that we're dividing up the piece into a bunch of small elements, and we're adding a contribution of each small element. So in particular, when we write ICM equals, now we can write it as m over L dx. That was our dm. And the distance of dm from the point we're computing the axis is x squared. Now the question is, what is our integration variable doing? Well, x is going from minus L over 2, that's at this end, to x equals plus L over 2 on the other end. So we have x minus L over 2, x equals plus L over 2. And now we've set up the integral for the moment of inertia, and the rest is just doing integral. Recall that the integral of dx, x squared, is x cubed over 3. And so this integral then simply becomes ICM equals m over L, x cubed over 3, evaluating from the limits minus L over 2 to x equals plus L over 2. Again, when you evaluate the limits, what we get is m over L. We have to put in L over 2 cubed divided by 3 minus L over 2 cubed divided by 3, and that's 1 over 2 cubed is an eighth, divide by a third, that's a 24th. 24th minus 24th is a 12th. And so what we get for ICM is m over L, a 12th L cubed, or 1/12 m L squared, is the moment of inertia about the center of mass of our rigid rod. And this is a measure of how the mass is distributed about this axis. I would now like to calculate the moment of inertia for a very thin disk. So we have a thin disk, and the radius of that disk is r, and it has a mass m. And I would like to calculate the moment of inertia for this disk. Now, let's just remind what point we're calculating about the center of mass. So our definition of moment of inertia was take a small element, mass element of the disk. In fact, we're going to see it doesn't have to be small. Take a mass element of the disk, that's useful, and multiply it by the perpendicular distance squared from the point we're calculating it. So the way I'll do it is I will choose a ring. I'm going to choose a ring of radius r, and now I'll make the ring a certain thickness, and this thickness is dr. Now, in this calculation, we're going to take a limit as dr goes to 0. So even though the ring has some finite thickness, its radius will eventually treat it as all the mass element at distance r from the center. So r will be our integration variable, and that will be equal to RCM, what we're calling RCM in our abstract result. Now, the dm is the tricky part. So what is the mass that's contained in this area, disk of radius r and thickness dr? Well, one way to think about that is here we didn't say this, but our thin disk is going to be uniform. And so we can describe the mass per unit area as the total mass divided by the area of the whole disk. And then we can say that the mass in that ring is equal to sigma, mass per area, times the area of the outer ring minus the area of the inner ring. Now, when we expand this out, dm, m over pi r squared, we get pi r squared plus 2r dr plus dr quantity squared minus pi r squared. And you can see those terms cancel. And so what I get is m times pi r squared. And in here, I have 2 pi r dr. Now, this is only order dr plus a second term that goes like pi dr squared. And so when I take this limit, as dr goes to 0, this term is much, much smaller than that term, and so I can say my mass element is m pi r squared times 2 pi r dr. Now, let's think about this term, why it makes sense. When we're shrinking our ring, so taking the limit as dr goes to 0, and the ring just becomes extremely thin ring at radius r, then this piece is the circumference, and this piece is just the width, and so it's no surprise that area is 2 pi r times d pi r dr in the limit. And now that enables us to write the moment of inertia about the center of mass, ICM. Let's pull out these constants, m pi r squared. Now we're integrating over the body. Let's hold off on the limits for the moment and put our values for dm. That's a 2 pi r dr. And we have our distance squared, which was, again, the radius r squared. And so the pi's will cancel. I have 2m over r squared times the integral of r cubed dr. Now we're supposedly integrating over the body, but what does that body integral actually mean? Well, what we're doing is we're taking a series of rings and adding them up as we go from the origin out to the radius of the whole disk. So the limits of our body integral with respect to our integration variable, we start with rings that essentially have no width. And we're integrating these, adding up the contribution of every ring until we get to rings of radius r. And our integration variable r cubed dr. Now this is an integral that's easy to do. That's r to the 4th over 4 between 0 and r equals r. And when we put that in, the 2 cancels the 4, and the pi we lost. So let's make sure this pi should be an m. So we have 2 over the 4 is 1/2 m r squared. And that is the moment of inertia of a disk about an axis passing through the center perpendicular to the plane of the disk. We defined moment of inertia of a rigid body already, and we often are interested in it because when we rotate a body about an axis, say an axis that's passing through the center of mass, then our kinetic energy depends on that moment of inertia through that axis. But we may also want to consider rotation about another axis. So suppose we consider an axis passing through close to the end, and we rotate the body around this axis. You can see from overhead, like that. Then we want to now consider how the mass is distributed about an axis that was parallel to the axis passing through the center of mass. So we'll now make a little calculation, but first we want to quote the theorem. So let's just draw an example of our rigid body, and let's take the center of mass, and let's consider an axis that's going perpendicular to the center of mass. We can think of the object as rotating about that axis, and now let's consider another axis passing through a different point, but also parallel to this axis, separated by a distance d. Then the key result that we want is that the moment of inertia about an axis passing perpendicular to the plane of the object through the axis s is equal to the moment of inertia about an axis passing through the center of mass, notice these are parallel axes, plus the mass of the object times the distance between the two parallel axes. And this is a result that is very useful when calculating moments of inertia. Of course, we could calculate the moment about any axis we wanted, and we'll see that in a moment. For example, we know that for a rod of length L, that the moment of inertia through the center of mass was 1/12 m. Let's call the length of the rod L. So we have a length L. And let's assume it's a uniform object, and we'll calculate a moment of inertia through an axis through the end. And so in this case, d is equal to L over 2. And so I about the end axis is 1/12 m L squared plus the mass times L over 2 squared. And a 12 plus a quarter is 1/3 m L squared. And that means that all you need to know is the moment through the center of mass, and you can calculate the moment through any other axis. Very useful theorem called the parallel axis theorem. Now, as I said, we can calculate the moment about S, and just to show you very quickly, if we pick S here, and we pick our little dm there, and we have a distance x, then the moment about S, and let's say that dm is equal to the total mass divided by the length times some little distance dx, then the moment is dm times x squared, where x will give us an integration variable, x prime goes from 0 to x prime equals L. And so we have for our dm, m over L, dx prime, remember that's our integration variable, and we have x squared, so that's x prime squared, And this is just the integral of x cubed over 3. So we have 1/3 m over L, x prime cubed, evaluated from 0 to L, and that comes out to 1/3 m L squared, and that's in agreement with the parallel axis theorem. And that's an example of parallel axis theorems. You can do the same thing with a disk or other objects. I would now like to calculate the moment of inertia of a uniform sphere. And it has a mass m and a radius r. Now, I'm going to look at 3 axes. So I'll call this the x-axis, the y-axis, and the z-axis. And first, let's calculate the moment about the z-axis. So if I write down our definition, and I'm going to calculate about the center of mass. So the moment about the z-axis, how do we do that? Well, we take a mass element. Now, I have to be a little bit careful here, because if you think about what is our perp for this mass element, it's actually x squared plus y squared squared. So the distance here, because it's going in a circle, the radius of that circle is x squared plus y squared. So we have x squared plus y squared. And we're integrating over the sphere. Now, this looks like a tough integral. But let's now look at what would the moment of inertia be about the x-axis. Well, the only difference here is I'm integrating now. First, if it's rotating about this axis, and I had my mass element, instead of x squared plus y squared about the z-axis, it's y squared plus z squared about the x-axis. That's the perpendicular distance. And if I calculate the moment of inertia about the y-axis, then same argument, I have z squared plus x squared. Now, the beauty of this problem, and in physics when we talk about beauty, we often talk about symmetry, is that by the symmetry of the sphere, all of these moments are equal. And let's call that ICM. Now, if I add these 3 pieces together, what do I get? So if I add ICMZ plus ICMX plus ICMY, I get 3 times the moment about the center of the axis. Now what happens when I add these 3 integrals? I get dm. If you'll notice, x squared appears twice, y squared appears twice, and z squared appears twice. So I get 2 times x squared plus y squared plus z squared. But x squared plus y squared plus z squared is the radius of a small sphere of thickness dr. And my mass element, now I have to integrate over the sphere. And so now our mass element, dm, is the volume density of this times the volume. Now, what is the volume density? Well, that's the total mass over 4/3 pi r cubed. And what is the volume of a sphere of radius r and thickness dr? That's 4 pi r squared dr. So if I put that into my expression, what I get, let's just get rid of the 4 pi's, and I get 3m over r cubed times r squared dr. And so our 3 ICM, I have a factor of 2. This integral becomes 2 times dm times r squared. And the dm is 3m r cubed r squared dr times another r squared. And what are we integrating over our r variable from? These shells, spherical shells that we're integrating outward, go from r equals 0 to r equal capital R. Notice that our 3 m's cancel, and we'll just write this as ICM equals factor 2 times m over r cubed times the integral of r to the 4th dr from 0 to r. And that's a simple integral to do. r to the 4th is r to the 5th divided by 5. And so we get 2 over 5 m r to the 5th over r cubed. And we conclude that the moment of inertia about any of the axes of the sphere is 2/5 m r squared. And in this calculation, it's a beautiful example of how we use the symmetry of the sphere to simplify very complicated integrals.
We did.
We would now like to compare the moment of inertia for a rigid body. Let's take an arbitrary rigid body about the center of mass. So let's say the rigid body is rotating about this axis. And what we'd like to compare that is to the moment of inertia, say, about a parallel axis that's also going through the rigid body. Now, let's recall how we define moment of inertia. We first choose a mass element dm. What I like to show is if this object is rotating about this axis, then what does that object do? Well, that object is undergoing a little bit of circular motion, and this distance here is what we call the perpendicular distance about that axis. And let's indicate this is for our element dm. So this perpendicular distance is what shows up in our definition for the center of mass moment of inertia about that axis. It's the integral of dm rcm perp. Now again, quantity squared. What is this distance? This is the perpendicular distance from our dm to the axis of rotation. Imagine it's doing a circle, and that's the radius of that circle. So if we recalculate the moment of inertia about another axis, then about this axis, the perpendicular distance here, that I'll write as rs perp. And you can see these perpendicular distances are not the same. And the moment of inertia about that other axis is equal to the integral of dm rs perp quantity squared. Now, how do we relate those perpendicular distances? Well, there's a couple of ways to do it. And notice that the distance between these axes is given by d. And I'm going to call this the distance rcm. Now, let's just call this the x direction. I'll call that x. So how do I relate these distances? Well, d is a fixed distance. And you can see from my diagram that rs perp is equal to d plus rcm x. And if I square this, I get d squared plus 2d rcm x plus rcm x squared. And that rcm x squared is precisely what we're calling the perpendicular distance. So when I put that into my moment of inertia is, I get dm times d squared plus 2d times rcm x plus, these parentheses, rcm perp squared. Now, I'll separate this into 3 terms. The first term is dm times d squared. This is an integral over the body. The second term is 2d, and I'm going to hold off on the integral because the 2d is the same for every piece, dm rcm x. And the third piece is integral over the body of dm r since RCMX is the R perp, I'll write it as R perp squared. And you can see that this term is precisely the moment of inertia about the center of mass. Now, what I'd like to focus on is this term, in particular, dm RCMX, that appears in our integral expression. Recall that we defined center of mass. We had the condition that the sum of mj RCMJ was 0. Now, for an integral relationship, this is dm RCMJ Cm equal to 0. So when you sum up the position of every object with respect to the vector from the center of mass to your dm element, 0. What does this say in terms of components? In terms of components, each component separately vanishes, so we have the condition that Cmx is 0. So that term is 0, which is precisely this term. That's 0. And so we can conclude that Is, now in this term, where d is the same piece for every object, so we're just pulling out the total mass. So it's n total, d squared, and let's remind ourselves that d is the distance between the two parallel axes plus the moment of inertia about the center of mass. And this result is called the parallel axis theorem.
Consider a rod of mass m. And suppose I apply a force to this rod, let's say a force like that. So we know that as a result of that applied force, the center of mass of the rod, which we can imagine is right at the center of the rod, will translate with some acceleration such that the vector f is equal to the mass of the rod times the acceleration of the center of mass. Now recall that for a rigid body, this equation will be true regardless of where on the rod I apply the force. So for example, if I draw the rod again over here, and I apply the same force vector f, but I apply it, let's say, on the right-hand side, I'll still have the same f equals ma. All I specify with f is its magnitude and direction. But for a rigid body, no matter where on the body I apply that force, the acceleration of the center of mass will be the same. Now, we know from experience, however, that the motion of the rod is different if I push it at the center or at one end or at the other end. The point is, though, that the motion, the overall translation of the object doesn't just involve the translation of the center of mass, but it also involves some rotation in general. So in fact, there's a theorem called Charles's theorem, which tells us that the most general displacement of a rigid body can be split into the translation of the center of mass and a rotation about the center of mass. Our F equals ma relation tells us how an applied force affects the first part, the translation of the center of mass. But how does that applied force affect the rotation of the rigid body? We'll see that this depends not only on the magnitude and direction of the force, but also on where the force is applied. Okay, that's different than the translation of the center of mass, which only depends upon what the force is. The rotation about the center of mass depends both upon the force itself and where on the object that is applied. In fact, in the next few lessons, we'll see that there's a special equation of motion for describing rotational motion. It's analogous to Newton's second law of motion, analogous to F equals ma, applying to rotational motion. And we write that relationship, this rotational equation of motion, is written as tau, which is a vector, is equal to I times alpha, which is a vector. So tau is a new quantity we haven't talked about before called the torque. It's a vector. I is the moment of inertia that we've already encountered. And alpha is the angular acceleration of the rotational motion. Now, tau is a sort of rotational analog to the force, and it depends on not just the force itself, but on where the force is applied. Computing the torque, tau, depends upon something called a vector product or cross product. It's a way of multiplying two vectors together to produce a third vector. And that way it's different than the dot product or scalar product that we discussed earlier, where we multiply two vectors together and get a scalar, or pure number. This is a different operation, the vector product or cross product. Torque is the first physical quantity we've encountered, but it won't be the last, that involves a cross product in its definition. And so before giving you a formal definition of torque, we'll first review the mathematics of cross products. So we'll do that in the next lesson. Now, the angular acceleration alpha tells us about how the rotational motion changes. Again, just like in F equals ma, where we could divide the two sides of this equation into dynamics and kinematics. Kinematics is telling us about a geometrical description of the motion, of translational motion, and the dynamics, F, is telling us about how the applied forces cause changes in the motion, changes in the kinematics. Likewise, for rotational motion, the angular acceleration alpha tells us about the geometry of the rotational motion, and specifically how the rotational motion is changing. And the torque is telling us about the application of forces and how that causes changes in the rotational motion. So that leaves one other quantity, which is the moment of inertia. And I want to talk about what that means for just a moment. So the term inertia in physics represents the resistance to an applied force. It tells us how difficult it is to change an object's motion. So, for example, suppose I have two blocks, one of mass m and another that's 10 times as massive, so 10m. Newton's second law, F equals ma, tells us that if I want to accelerate the heavier mass to the same rate that I do with a smaller mass, I'll need to apply a force that's 10 times larger. So for translational motion, the mass m represents the notion of inertia, the resistance to a force. It tells us how much force we have to apply to achieve a certain change in motion. Now, for rotational motion, that role is played by the moment of inertia, I. That tells us how difficult it is to change the rotation of an object. If I increase the moment of inertia by a factor of 10, then I'll need a torque that is 10 times larger in order to achieve the same change in rotational motion, the same angular acceleration. But recall that our definition of moment of inertia for some rigid body is if I break up the rigid body into a bunch of little pieces, and for each piece I take the product of the mass of that piece, delta mj, times the perpendicular distance of that piece from the rotation axis, I'll call that r sub j, and if I sum that over the entire object, the entire body, that gives me my moment of inertia. Well, this is a r squared. So it's the mass of each element times the distance of the axis squared, delta mj times rj squared. Now, I can increase the moment of inertia by a factor of 10 by increasing the total mass of the object. But you can see from this equation that I can also do it with the same mass by changing the location of the mass. If I increase the r's If I move the mass, the same mass, but I move it to be farther away from the rotation axis, that also achieves an increase in the moment of inertia. So what that tells us is that for rotational motion, it's not just the amount of mass that matters, but also how that mass is distributed. Okay, so in that sense, rotational inertia is different than translational inertia. For translational motion, all that matters is the mass. If I increase the mass by a factor of 10, then it will become a factor of 10 more difficult to get that object to accelerate. I need a factor of 10 larger force. But with rotational motion, I can increase the notion of inertia. I can make it more difficult to change the rotational motion, either by changing the mass, by increasing it, or by making the distribution mass be further away from the rotation axis. So as an example, imagine if you were rolling a wheel up a hill. It's different if I have a wheel whose mass is distributed evenly over the whole disk, or if I have all of the mass in the rim. If all of the mass is in the rim, then from this equation we see the moment of inertia is larger for the same amount of total mass. And so it's much more difficult to roll a wheel up the hill if all of the mass is in the rim than it is if the mass is distributed evenly over the wheel. So our rotational equivalent to Newton's second law is tau equals I alpha, the torque equals the moment of inertia times the angular acceleration. In the next few lessons, we'll see how torque is defined, and we'll derive this expression for the dynamics of rotational motion and see how to apply it.
There's another vector operation, which we call the vector product. And sometimes this operation is called the cross product. And this is taking two vectors, A, the operation cross B, and this will give a new vector C. And now we want to define that new vector C. So let's draw a three-dimensional picture where we have a plane. And on this plane, we have two vectors, A and B. And those vectors are forming an angle theta between them. Now, a plane defines two unit normals. I'll draw one up, which I'm going to call n hat right-hand rule. And the reason for that right-hand rule is if we take A cross B, then our right-hand thumb is pointing in the perpendicular direction to the plane. Now, I could have chosen a unit vector down, n hat left-hand rule, and this would correspond to taking my left hand and having A cross B pointing down. So the way we're going to define our cross product is with the right-hand rule. And so we define it like this, that the vector C has magnitude, the magnitude of A times sine of theta, the magnitude of B, and its direction is given by the right-hand rule. Now, one of the reasons for this definition is, let's draw a vector A and a vector B. When you have two vectors, they define a magnitude in the following way, that we can think about any two vectors define an area of a parallelogram. And we can define that area as follows. Let's drop a perpendicular, and let's call this B perp. Then the area, which is a positive quantity, is given by, and by the way, our angle theta here will be always positive, so we're going to make it 0 theta pi. And that way sine of theta is always a positive quantity. The area is the height, so that's B perp, times the base, which is the magnitude of A. And so we can write that as A, and B, the magnitude of B perp is B sine theta. So this quantity, B sine theta, is precisely what's occurring there. So the magnitude of C is equal to the area formed by the vectors A and B, and we have a choice of which way we want to pick C to point, and that's where, as a convention, we're choosing the right-hand rule. Now, again, there's a symmetry here, in that I can also define the area of that triangle in the following way. Let's write this the theta. Instead of taking how much of B is perpendicular to the direction of A, let's drop perpendicular this way and write that as A perp. And then the same area can be expressed as the magnitude of, well, we'll express it as A perp times B. And A perp is the magnitude of A sine theta times the magnitude of B. And that's our same definition as before. And so you see A sine theta is appearing over here. So in either choice, our vector operation says take any two vectors. Any two vectors forms a parallelogram. The area of that parallelogram is the magnitude of the vector product, and the direction of this new vector C is given by the right-hand rule with respect to that parallelogram in that sense. So when we have a vector product of two vectors, A cross B equals C, let's compute that vector product in different coordinate systems. So let's begin by choosing two vectors I hat and J hat. And notice they're at a right angle, and because there's a unit vector, the area here is equal to 1. And I want to define K hat to be equal to I hat cross J hat. Now, our angle theta here was 90 degrees. And so if I use the right-hand rule, then I hat cross J hat is, the right-handed unit normal is out of the plane of the figure. And so I would write K hat like that. And notice K hat is out of plane of figure. And because I use my right-hand rule, this is what we call a right-handed coordinate system. Now, there's something very nice about this cross product definition. Notice that there's a cyclic order. I, J, K is a cyclic order. And if you interchange any two, for example, J, I, K, that's anticyclic. And the cross products satisfy this cyclic rule in that J cross K hat is I hat. And notice J, K, I maintains that cyclic order. And K hat cross I hat is J hat. K, I, J maintains that cyclic order. But because of the way we define a cross product in general, A cross B is minus B cross A, because now you're using the opposite direction, so there's a minus sign. And therefore, any anti-cyclic permutation of these unit vectors, as an example, K hat cross J hat, has to be, notice I've, what's called is minus I hat. That's anti-commutative property of the cross product. Similarly, I hat cross K hat is minus J hat. And lastly, J hat cross I hat is minus k hat. And so, in fact, you only need to know one, and this idea of cyclic and anticyclic, to be able to write down all of the other 6. So we have 1, 2, 3, 4, 5, 6. Now, when you want to compute the cross products in Cartesian coordinates, for instance, it can be a little bit messy. There's going to be a lot of terms. If I write a vector A as ax I hat plus ay j hat plus az k hat, and I write a vector B as bx I hat plus by j hat plus bz k hat, and now I want to compute the cross product of these vectors to get the new one, notice that there's going to be 6 terms because I have I hat. Well, we actually should say one more thing, that I hat cross I hat, the angle between these two vectors is 0. There's no perpendicular projection, so that's 0, as is j hat cross j hat, k hat cross k hat. So of these 9 parts, when we take the cross product, 3 of them will be 0 by this rule, and we'll apply our cyclic or anticyclic rules for the others. And so what we have here, let's just do it in, so C equals A cross B. And now let's just go one by one. I hat cross I hat. That's 0. The vectors, there's no perpendicular part. The area formed by these two vectors is 0. I hat cross j hat. That's cyclic. Ij is plus k hat. So our first non-zero term is ax by k hat. I hat cross j hat. And now let's do I hat cross k hat. Notice that's anticyclic, ik minus j. So our next term is minus ax bz j hat. So there's the first two. And now let's just continue this process. J hat cross I hat. That's anticyclic. So we have minus ay bx k hat. Ay j hat cross bx I hat. J hat cross j hat. That's 0. So we have no contribution there. And j hat cross k hat, that is cyclic. So that's plus ay bz k hat. And now we have our last two terms. K hat cross I hat, that's cyclic. So that's plus az bx j hat. K hat cross j hat, that's anticyclic. So there's a minus I hat. So it's minus az by I hat. And finally, k hat cross k hat, well, that's also 0. So we have 6 terms, and we can collect them equal to ax by minus, well, let's check this one. Here we use the wrong symbol here. We have to be a little bit careful here. Ay cross bz is j hat cross k hat. That's plus I hat. So we have ax by minus ay bx k hat. And now let's look at the I hat terms. I'll just check those off. We have ay bz minus az by I hat. And check those two terms off. And lastly, we have az bx minus ax bz. So we have az bx minus ax bz, and that's j hat. And that's how we calculate the cross product in Cartesian coordinates.
God help.
Let's think about calculating torque. I have a force F being applied to an object, and that object is pivoted at a point Q. I'll define R as the vector from the pivot point Q to the point of the application of the force. Torque is defined as the cross product R cross F, which we can also write as R times F times the sine of theta. But what does that mean? I'll introduce 2 different intuitive ways of understanding this mathematical expression. First, we can think about this as the magnitude of F times the quantity R sine theta. If we look at the direction of the force, then it is easy to see that R sine theta is just the part of R that is perpendicular to the force. So here, the torque is equal to the magnitude of the force times the magnitude of this perpendicular part of the vector R. This perpendicular portion of the distance vector R is often referred to as the moment arm. We can instead group F with sine theta. So this means that we're thinking of the cross product as the distance R multiplied by F sine theta, the component of the force F that's perpendicular to the position vector R. Here, I'm calculating torque as the distance between the pivot point and where the force is applied times the perpendicular part of the force. Be very careful about the sine theta term. In many cases, the angle theta that is given in the problem is not the angle that is used in the expression. In this example, F times the sine of theta will actually give the parallel component of the force. Therefore, it is much better to remember to take the perpendicular component rather than just memorizing sine of theta.
We would now like to consider a system of particles, and let's draw them as 1, 2, 3, and let's refer to this one as the J particle of mass mj. And these particles, system of particles, is in a gravitational field. And I would like to consider the torque about some point S for this system of particles. In particular, I'd like to know, how do I treat the gravitational force that's acting on all of these individual particles? Well, the way we'll analyze this is recall that the definition of torque about some point, now we have n particles labeled by index j. It's a vector from the place we're calculating the torque to where the jth particle is located. So we draw that vector rsj, and we cross that with the force that's acting on the jth particle, which in this case is the gravitational force mjg. And this is the torque about S, and it's this complicated sum. But the sum will simplify in the following way. Let's just write out a couple terms to see what it actually looks like. So we have r s1 cross n1g plus r s2 cross n2g, and we just keep on going for the n terms. Now, the quantity m1 is a scalar, units of kilograms in SI units, but the cross product is between this vector and that vector. So I can actually rewrite this as m1 rs1 cross g plus m2 rs2 cross g, etc. And you see that the g term is the same for every single object. So I can write this sum, j goes from 1 to n, as mj rsj, and pull the g out of the sum because every term has the same g in the cross product. Now, let's focus on the meaning of this sum, where we're weighting position by mass. Recall that if you have the center of mass of an object, and we want to find out where is the location of the center of mass with respect to point S, then we can calculate this vector, rscm, by our definition that the location of the center of mass with respect to S is given by the sum, j goes from 1 to n, of mj rsj, and we divide that by the total mass, mj. We'll denote this term by m total for the total mass. So what we see here is the total mass times RSCM is equal to exactly the sum that we have in that expression NJRSJ. That's precisely that term. And so we can conclude that the torque about the center of mass is n total RSCM cross G. Now remember again, n total is a scalar. The cross product is between these two vectors. And so finally, we write this as RSCM cross n total G. And this is how we apply the gravitational force to a system of particles. Now, what does that mean? Well, let's just denote our system like this. And let's say here's the center of mass, and here's the point S. So what we need to do is we need to draw the vector RSCM and apply all the gravitational force at the center of mass. And then our torque about S is the vector RS to where the force is acting across n total G. So in conclusion, when you have a rigid body or a system of particles, and you want to calculate the torque due to a uniform gravitational field, then we place the total gravitational force is acting at the center of mass. And that gives us the torque about S to the individual torques of the system of the gravitational force about S. All the force is placed at the center of mass. We now would like to consider the motion of a rigid body that's undergoing angular acceleration about some axis. So let's consider for simplicity a disk. And we have an axis that's passing through some point S. Here it's the center, but that's not crucial. And we want to consider the fact that this object, we'll call this our z-axis, k hat unit vector in that direction, so it's pointing up. And this object is undergoing an angular acceleration where alpha z is the z component of the angular acceleration. Now, what we'd like to consider is the torque on this object. So the way we'll do it is we'll divide the object into a bunch of pieces, and let's identify a piece here as delta nj. That's that piece. And this piece has some force acting on it. Now, this force can be a vector, but the important thing to realize is that this force is only the external force, because we've already going to make the assumption that all internal torques cancel in pairs, and we'll show that in the video a little bit later. So we're only considering the external forces that are acting on this element, and recall that we have the vector rs to j is the vector from point S to where this mass element is. And now what we'd like to do is calculate the torque. In general, torque is given by the expression, we'll sum over all the elements, j goes from 1 to n, and it's the cross product of our sj cross fj external. Now, our goal here is only to calculate the z component of the torque. So we can simplify our understanding a little bit by writing out this vector f external j as a component in the plane, and in order to describe that, we'll choose some unit vectors, r hat, theta hat going into the plane. We'll make another picture in a moment. So our vector can have a r component, and I'll keep the external in there. It can have a theta hat component, and it can also have a z component. But recall that a cross product is always perpendicular to either of the elements. So when I cross r with anything in the k direction, then that component will give a component that's not in the z direction, and so I can ignore that. So my first simplification is to say that the z component will only come from the cross product of rsj with these two pieces. So that's cross fjr r hat plus fj theta theta hat. Now again, we can make another simplification, and perhaps here it's helpful to have another overhead view. And here's our mass element, delta nj. That's our vector from S, from the center to delta nj. We have unit vectors r hat and theta hat. And so we see that this vector rsj has some length in the r hat direction. Now, we're picking S as the origin of our coordinate system. This can generalize, so we don't worry about if the object is not symmetric. So when you take the cross product of r hat versus r hat, that also is 0. And so we see our simplification is quite nice, that the z component of the torque is only arising from the sum of j goes from 1 to n of rsj. We'll write this all as vectors, r hat cross fj theta theta hat. Now, again, even if our external force, by the way, we're dropping external, we could always say external, but I think for simplicity, we'll now drop the external. And what we're considering is just the component of the force. We can write that fj, this is a little complicated theta, just the theta hat component of that force. This is the only piece of the force that matters in contributing to the z component of the torque. And this cross product is very direct because we've chosen a right-handed system where r hat cross theta hat is k hat. So we see that this becomes j equals 1 to n of rsj fj theta in the k hat direction. Now, that's just the calculation of the torque, but as always, it's crucial to understand where Newton's second law appears in these calculations. And Newton's second law for this mass element delta nj, so the second law, is telling us that the tangential force is proportional to the mass element times the tangential acceleration of that mass element. Now, for this type of rotation about the z-axis, so when we're rotating about that z-axis, we know that a j theta, so the acceleration of this tangential element, is just proportional to rj, the distance from, well, we call that rsj, so how far away from the center. And here's the key thing, it's also proportional to the z component of the angular acceleration. And every mass element in the body has the same alpha z. And so our sum for the torque can now be written in the following way, the z component of the torque. Now I'm going to do something here, which is I'll write j equals 1 to n, a parenthesis mark. I have one of the rsj's, I have another rsj, a delta nj, so I have delta nj, rsj squared, but every single component has the same alpha z, and we're in the k hat direction. Now, because we have a continuous body, we have to again consider a limit. So let's call the limit as delta nj goes to 0 of this sum, delta nj rsj squared. Well, that's an integral over the body of dm rs squared and we identified that before as the moment of inertia about the z-axis. So the quantity in parentheses is just a measure of the mass distribution about the axis. You see the r squared, the delta mj. And so in conclusion, we have that the z component of the torque is equal to is alpha z k hat, which is now a vector because that's the vector alpha. And this is our crucial result for a body that's rotating about the z-axis. This result can generalize to not just a disk, but any body that's looking at the z component for this fixed axis rotation. We'd like to consider torques on a body. Let's draw an arbitrary body, and let's consider a point S that we're about to calculate the torque. Now, we know that forces on the body can be both internal and external, and we'd like to show that all internal torques will cancel in pairs. The way we'll do that is suppose we pick a object, we'll label it with mass mi, and another object, we'll label that with mass mj. These are small mass elements in the body, and we'd like to know something about the internal forces. Now, let's make the assumption, and this is the key property, that the force due to this interaction between j from the ith particle pointing that way, and here's the Newton's third law pair, that these forces are directed along the line connecting the two bodies. With this assumption, we'll now show that the torque due to these two internal forces, Newton's third law pairs, will cancel. So let's calculate that out. So we draw our vector from RSI and our other vector RSJ. And now we're in position to add these two torques. So we have the torque on S due to this pair is equal to the sum of RSI cross FJI plus RS, that's an R, make sure we get that right. We have RSJ cross FIJ. Now the third law pair says FJI is equal to minus Fij. And so if we substitute, let's put the minus sign over here, we get RSI minus RSJ cross FJI. Now, let's look at this vector in particular. We can draw it again over here just to see it. Here's S, here is RSI, here is the vector RS, that's RSJ. And we want to now consider the vector RSI minus RSJ. Notice that this vector is directed along the lines connecting the ith and the jth particle. And we made an assumption that FJI is also along that line. So these two vectors, in this particular case, are either parallel or antiparallel. And hence, the torque due to the sum of these internal forces cancel in pairs. And this means we only need to address the torque due to external forces that are acting on individual elements in the body.
Let's determine the moment of inertia of a big wheel. Here we have a big wheel, and on the side it's attached here at the center, and there's a string going around here, and on that string is a little mass hanging. And our disk here has a radius r, and we now want to know, in a little experiment, what the moment of inertia is of this disk. And what we have to do is we have to drop this mass to the ground, and we need to measure what the height is here, and we need to measure how long it takes to drop, so we need to measure t. So how are we going to go about that? Well, the moment of inertia, that probably has something to do with the torque of this wheel, so we have to start doing a torque analysis. So torque about the center of mass equals moment of inertia about the center of mass times the angular acceleration. And we need to recall that the torque is the product of the radius times the perpendicular force. So we're going to have r here, and then the force that's acting on this wheel here is actually this tension force here. So we're going to have rt here. And now we need to look at how things are actually moving with respect to a coordinate system. So if I pull, or if I let this mass drop, the disk is going to spin clockwise. So we're going to have theta hat going this way. And if theta hat is going clockwise, my k hat vector is going to go into the board. And if k hat's going to go there, well then, and it's rotating clockwise, the angular acceleration is going to go in the k hat direction. And if that is the case, then our torque is going to follow suit. So torque also goes into the board. And so that means here we're going to deal with k hat direction, and we're going to have I, cm, and then alpha z in the k hat direction. Okay, so we can solve this for I, rt over alpha z. Okay, well, that's pretty good, but we have two unknowns in here, the t and the alpha z, and we can use some other concepts to actually get information on those. The t, as you can guess already, plays a role here in this massless string, so we can do a quick free body diagram and an F equals ma analysis to get to that tension force. So we have our little mass m here, gravity is acting on it, and we have this tension force here, and we're going to put j hat down. So we're going to get mg minus t equals ma. It's only going to go in the y direction, so we can just leave it here. We can do this. We can solve this for t, and then we have mg minus a. Okay, good. So we have that. Now about the angular acceleration, and whenever there's a string going around a disk, then we of course have a constraint condition, because the linear acceleration of this little mass going down is related to the radius of the disk times the angular acceleration. So we can solve this for alpha, and then we have a over r. Now, so let's put that in here. R, then we have mg minus a over a, and then we get another r here, and we can write that just a little bit more compact, mr squared g over a minus 1. Good. So now we have one last hurdle, namely that a here. That a we can't measure. I said in the beginning we want to make an experiment. Actually, we need that experiment because we can't otherwise get to this a. So what we need is a relation that connects what we can measure, which is the time. It falls down this height here to the acceleration of this block. And of course, that comes from one-dimensional kinematics. And we know that h equals 1/2 a t squared. So we can solve that for a, 2h over t squared. And now we can stick that in here. And we have mr squared and gt squared over 2h minus 1. And let's just write this here again. And that is our final solution. So now we have only measurable quantities here. The t we can measure. We just need a stopwatch. And the h we can measure as well. And this actually already resembles, if you know the theoretical, this already resembles the theoretical solution, which of course is for a disk, 1/2 mr squared. So that's what one expects for a disk. And you see that we're very close. So this term here is probably something like 1.5, or should better come out to be 1.5, because if we subtract 1, we get to that half here. And you can use it to, in return, you can also use it to predict the time it takes to fall down if you know what the height is, or vice versa.
Let's consider a very famous problem, the Atwood machine. We have a pulley, A, suspended from the ceiling, and a rope is wrapped around the pulley. And on each side of the rope, there's different masses. So here's block 1 and block 2. And we can say here, it doesn't matter, but we'll say that M2 is bigger than M1. And that gives us some intuition that we expect block 2 to go down and block 1 to go up. Now, in this problem, there is friction between the rope and the pulley, so the rope is not sliding. And what that means is that the pulley will rotate. And also the mass of the pulley is not 0. So these were all assumptions we made way back when we were analyzing Newton's second law. But now we have to take into account that there's some rotational inertia to make the pulley start to have angular acceleration. So what we'd like to do is to identify our three objects, mass 1, the pulley, and mass 2. And for mass 1 and mass 2, use Newton's second law. For the pulley, we'll use our torque relationships. So let's begin by drawing our free body diagrams for object 1. So we have tension in the rope, pulling object 1 up. We have gravitational force down. And here, it doesn't matter which way I'm going to choose my unit vectors, because I have this idea that M2 is bigger than M1. I'm just going to choose j hat 1 up. Now, for block 2, I have M2G. Now, here's the place where lots of people get tripped up. In the past, we've been assuming that the tension in the rope is uniform everywhere. In this problem, because the rope is not slipping and the pulley is not massless, the tension is not constant everywhere in the rope. And we'll see more reasons why that can't be the case. So I'll have to identify a different tension on the other side, T2, pulling the rope, pulling the block up. And I'm going to choose j hat 2 down. Notice my unit vectors are chosen in opposite directions. The reason for that is that there's a constraint here that as block 2 goes down, block 1 goes up. If the acceleration of block 2 is positive, the acceleration of block 1 will also be positive if I choose unit vector pointing up. So now I can write Newton's second law for both of these. So for block 2, positive down, M2G minus T2 equals M2A. It's the same acceleration in the rope. A is equal to A1 equals A2. They're all positive. And for 2, notice I have positive up minus M1G equals M1A. So far, these are my two equations. I have three unknowns, T1, T2, and the accelerations, and only two equations. Now let's analyze the pulley. So we have our pulley A, and what are the forces on the pulley? Well, forces and torques are a little bit different, but let's just draw our forces first. There's a tension holding it up. We'll call that T3 from this rope pulling it up. Now, here's where we have to be careful. Rope 1 is pulling the pulley down. That's what we call T1. So we draw T1 on this side, and the same rope on the other side is pulling the pulley down. Notice that it is a different T2. Now, this brings us to what we called our rotational coordinate system. I do expect that the angular acceleration of the pulley, so as the pulley rotates in this problem, I expect that it's rotating in the direction, like my right-hand rule, this way. And so I expect to see the alpha pointing like that. What I'll do is I'll choose a coordinate system for an angle theta, and that will make positive direction like that for my rotational coordinate system. Now, when we write torque equals the moment of inertia of the pulley times the angular acceleration, we have two torques. The radius is r, radius is of r, and if we're calculating the torque about the center of the pulley, we'll call that point O, then each of these torques are in different directions. So for instance, we would have to take for T1 going down, and this vector from origin to where T1 is acting, we can extend that force, and we see that that torque is pointing in the direction like that, and that's opposite our sign here. So this torque minus T1r is negative. What about the torque from the other force, T2? Again, we would draw that vector. Let's draw them over here. We have T2 pointing down. The point O is there. The vector from O to 2 is pointing like that. We extend that vector. We put the arrow like that. And we see that this one is pointing in our positive direction. So we have a plus T2r equals IA alpha. Now, right away, we can see why the tension in the strings is not the same. Because if these tensions were the same, this quantity would be 0. But the tensions can't be the same because the pulley is rotating. And that rotational inertia of the pulley is coming from the fact that the two torques are not the same on both sides. So we now have our last equation here, T2r minus T1r equals IA alpha. But notice that I've introduced another variable here. So again, I have 4 equations and only 3 unknowns. We still have one last constraint. Because the rope is sliding along the pulley and the radius is r, we know that a point on the rim of the pulley has acceleration a of the rope, but the pulley has an alpha angular acceleration, so our constraint condition here is plus r alpha. Now, why did I put a plus sign? Because when the pulley is rotating in the direction shown, alpha will be positive. This quantity of torque will be bigger than this one. And so we'll have a positive alpha. When I chose j hat 1 up and j hat 2 down, that made all of my accelerations positive, and so I end with a plus sign. If I had reversed my choice of unit vectors, then this would be a minus sign. So you have to be extremely careful by making sure that the directions you chose for the linear force diagrams that give us A and the direction we chose in our rotational coordinate system are consistent when we choose to relate the constraints between them. So that's our last condition, that A equals R alpha. So I now have 4 equations and 4 unknowns, and if I want to solve for the acceleration a, then I have to need a strategy here. And what I'll do to find a is I'll use this equation as my backbone. Why did I do that? Because I have the unknowns t2, t1, and alpha, and I have separate equations that relate alpha to a, and t1 to a, and t2 to a. And so I can solve for t2 and substitute in here. I'll need a little room. So I get that t2 is m2g plus m2a, minus m2a times r. Now t1 is m1a plus m1g times r, and that's equal to IA times alpha, which is a over r. So I'll now collect all of my a terms over here, and so I get m2gr plus minus m1gr, this term and this term, is equal to a times IA over r. Notice I have 2 plus signs here, so I get m1 plus m2 times r. And I therefore conclude, we'll put it over here, that the acceleration a is equal to m2 minus m1 gr divided by IA over r plus m1 plus m2 r. Now, when I have this result, let's just check a number of things first. Notice that if m2 is bigger than m1, a will be positive, which is what I expected. Dimensionally, we have m2gr. Down here, m2r, so this first term will have dimensions of acceleration g. Now over here we have IA over r, but remember moment of inertia is m times r squared, so this also has the dimensions of mass and radius, and so I have confidence dimensionally and the sign of a that this is the correct answer. And that's how we solve the Atwood machine.
How do we solve problems involving massive pulleys using Newton's laws? As a simple example, let's look at this problem consisting of a block of mass m1 hanging from a massive pulley that has a moment of inertia I and radius r. We'll find the acceleration of the block a1 and the angular acceleration of the massive pulley alpha. It is critical to remember that the first step in solving these problems is to define the positive x and y directions, and the positive direction of rotation. In two-dimensional problems, you're free to define any direction to be positive. Here, we'll set our positive x and positive y like this. Once we pick x and y, the direction of the positive rotation is now also defined by the right-hand rule. You'll see shortly that finding positive directions at the beginning will save you from a negative sign nightmare later on. Now let's write down Newton's laws for the different parts of the system. First, for the block, we will write down the linear version of Newton's second law. For the sum of forces, we have gravity pointing down and tension pointing up. According to the convention we just defined, T1 is positive and M1g is negative. Notice that since the block is accelerating, T1 minus M1g is not 0, but is equal to M1a1. Notice that here we've set the signs for tension and weight, but we don't yet know which way the block is accelerating, so we just start by writing M1a1, and if in the end we get that a1 is negative, we'll know that it's actually accelerating in the negative direction. Now, let's look at the pulley. Newton's second law in its rotational form is tau is equal to I alpha. For a normal pulley, the string is always tangential to the side of the pulley, so R and F are perpendicular, so that means the torque is just T1 times R. What's the sign of this term? Well, according to the positive direction that we defined, this torque is positive. Again, we'll leave the sign of the I alpha term to be positive, and alpha will turn out to be either positive or negative. Finally, we need to connect these two equations. Because the block is connected to the pulley using an ideal taut inextensible rope, A1 is going to be related to alpha. We just need to figure out exactly how they're related. In other words, we need to write down the constraint condition. Let's say that the block, hypothetically, is moving upwards. In this case, what's happening to the pulley? It must be spinning clockwise to pull the rope up as the block goes in. So it has a clockwise angular velocity, which, according to our convention, is negative. In fact, if the pulley rotates a full turn in the clockwise negative direction, the angle changes by negative 2 pi. And 2 pi times r of the rope will be pulled up. So we can write that delta y is equal to negative r delta theta. Or, taking some derivatives, a1 is equal to negative r times alpha. After setting the sign conventions, writing Newton's laws for different parts of the system, and then writing down the constraint condition, we have 3 equations and 3 unknowns, for which we can now solve.
When we used our energy principle, suppose we have an object that starts at a height h naught, and this object is dropped, and when it gets to the ground, it has some final velocity. And when we applied our energy principle, assuming that there was no air resistance, what we saw was that the change in kinetic energy plus the change in potential energy was 0, so we had 0 was equal to delta k plus delta u, and we saw that the kinetic energy changed by 1/2 mv squared, and the potential energy changed by minus mg h naught, so we can compute the velocity of the object as it's falling, given by square root of 2 g h naught. Now that we're considering kinetic energy of rotation, recall that we showed that the kinetic energy of a pure rotation about a fixed axis was 1/2 the moment of inertia about that axis times the angular speed squared. We now would like to apply our energy principle to include rotational kinetic energy along with the translational kinetic energy. And the example that we want to look at is something very simple. Suppose we have a pulley. Now our pulley has a mass p, and we'll say it has a moment of inertia of the pulley about the fixed axis passing through the center of the pulley. And we have a mass 1 and another block 2. And let's suppose that we release this system, and for the moment let's make this surface frictionless. And suppose that block 2 falls down a certain distance. So in the final state, block 2 will have dropped the distance h final from its initial position. And what we'd like to consider is find the velocity final of block 2. So we begin in the same way that we've done this before by considering our energy diagrams. And so we'll have an initial state. And in our initial state, what we'll do is we'll just have the initial 1, 2, and I'm going to choose u equals 0. Here's my pulley. And everything is at rest. And so in the initial state, the initial energy, I initial, k initial, plus u initial, is 0. And in our final state, we have the pulley is rotating with omega final. Block 1 is moving with a velocity v final 1. And block 2 is also moving with v2 final. And let's just suppose that this was our u equals 0 position. And although it's not so clear in the diagram, u final, it has moved down height h final. So what is the energy in our final state? Well, we have to consider all the different pieces. We have block 1, 1/2 m1 v1 final squared. We have the motion of block 2, 1/2 m2 v2 final squared. And we also have the kinetic energy of the pulley, which is given by 1/2 I about the pulley omega final squared. And what about our final potential energy? Well, we dropped the height h final, so we have block 2 has moved minus m2 g h final. And now we have our two energy states, and what we'd like to consider is to apply the energy principle just like we applied it for this simple case. But before we do that, there is a constraint condition that because the rope is fixed in length, as block 1 moves, the pulley is rotating and block 2 is moving. What we'll have is fixed and not slipping. So as the rope moves around the pulley is moving with the same motion as the rope, and the rope is moving with the speeds of block 1 and 2. So we see that v1 final is equal to v2 final. And now what about the pulley? If this is radius r, we know that the velocity of a point on the rim of a disk is moving with the speed of the rope, which is the speed of block 1 and block 2, so that's r omega final. And so that makes our final energy, let's now gather terms. The velocities are the same, so we have 1/2 m1 plus m2, and we'll just call this v final for simplicity. 1/2 m2 times v final squared, that accounts for these two terms. And we have the moment of inertia, kinetic energy associated with the wheel, which is 1/2 I omega final squared, which is v final squared over r squared minus m2 g h final. And so now we can solve our energy principle, which is because we're assuming everything's frictionless, we have 0 equals E final minus E initial, implies that E final equals E initial. And we chose our initial potential energy to be 0. So, of course, that's just a choice of constant. So I can now solve this equation by setting E final equal to 0. That's the same statement. And then you can see algebraically, I can solve for V final. And what I get is I'm just going to write all these terms over. I get M2 G H final. I'm going to divide by this common coefficient, 1/2 M1 plus M2 plus the moment of inertia divided by radius squared. And I now have to take the square root of the whole thing. And that's how I can find the velocity of block 2 when it's dropped down a certain distance h final. So here we generalized our energy approach to include rotational kinetic energy. I would like to now analyze the motion of a system of particles that has both translational and rotational motion. So I'm going to consider a pulley, and the pulley has radius r.
Gotta go piss first. And we are back.
And there is a string wrapped around the pulley, and a block of object 1 that's on a plane, and another block of object 2. And as object 2 falls down, the pulley rotates, and object 1 moves to the right. And there's a coefficient of friction between these block 1 and the surface. Now, in order to analyze this problem, I'm going to apply, for the pulley, our torque equals ICM alpha, and for each of the blocks, I'll apply F1 equals M1 A1, and F2 equals M2 A2. But the important thing to realize is that these three quantities, the acceleration of block 1, the acceleration of block 2, and the angular acceleration of the pulley, are constrained because the string is not slipping around the pulley. And so let's begin to analyze this type of problem. So we'll start with the torque principle. Now what's crucial in all of these problems is that we're relating two different quantities, vectors on both sides. The physics quantities have definite direction, and our alpha A1 and A2 as vectors are determined by our choice of coordinates. So what I'd like to do is draw a coordinate system, a rotational coordinate system. Now the way I'll do it is I'll draw an angle theta, and now I have to draw a right-hand rule, so my angle theta will look as though it's going into the plane of the figure, and so I write cross n hat right-hand rule, and I'm going to just define that to be k hat. Now what that allows me to do, when I write my point S here will be Cm, so I'm going to calculate this about the center of mass, and I get ICM alpha. As soon as I draw the coordinate system, then this side becomes the vector alpha z k hat, where alpha z is the z component of the angular acceleration. And technically, the reason this angle is there is because this is the second derivative of that angle, and that's well defined now. So the next step is to define the force that do what we call a torque diagram. So this is my rotational coordinate system. The next step is to construct a torque diagram, and the way we do that is we draw the object, we indicate our rotational coordinate system. I don't have to put the theta anymore. Now, here's a subtle point. I'm going to draw the rope that is connected to the pulley as part of my system. This is the part where the tension here, I'll call that T2, and over here, this is the tension T1. Now, on the pulley, there's a gravitational force, and there's some pivot force on this pulley. And now what I want to consider is the torque about the CM. Now, the pivot force, F pivot, and the gravitational force produce no torque about the pivot. So I'm just going to eliminate those for the moment and just focus on the torque due to T1 and T2. So I draw my vector RS T1 and my vector RS T2. So this is what a torque diagram consists of. Let's summarize it. It's our system, the relevant forces that are producing torque, vectors from the point we're calculating the torque, our S is, it's a little easier to write, S is the center of mass, and the vector from where we're calculating torque to where the force is active. And now, when we calculate the cross product of RS and T, we put these two vectors tail to tail, and notice that this vector is giving us a torque out of the board. Our positive direction is into the board, so over here we have minus T1 R. Whereas T2, when we put these two vectors RS T2, and we calculate that torque is into the board, which is our positive direction, and so that's plus T2 R2. And now in our torque principle, we set these two sides equal, and we have minus T1 R plus T2 R equals ICM alpha Z. Now, this is our first equation, but it requires some type of thought. For the first thing, we see that the tension T2 is equal to ICM over R alpha Z plus T1. So the tensions on the side are not equal. Now, when we studied pulleys earlier in the semester, we imposed a condition that the pulley was frictionless, which meant that the rope was sliding along the pulley, and there was no rotation in the pulley, so there was no contribution to alpha. And in that case, T2 would be equal to T1. We also could make a slightly different statement. We could say, suppose the mass of the pulley were very, very small, an extremely light pulley. Then ICM would be 0, and again, T2 would be equal to T1. So when we were dealing with either massless pulleys or ropes that were slipping frictionlessly along the pulley, the tension on both sides was equal. Now, something different is happening. We need to apply a greater torque here than T1 because there is rotational inertia. We're causing the pulley to accelerate. So the torque from T2 has to be bigger than the torque from T1, and therefore T2 is bigger than T1. So that is a very important way to apply the torque principle. When T2 is bigger than T1, alpha will be positive, and a positive angular acceleration is giving a rotation in which our angle theta is not only increasing, but its second derivative is positive. So that's crucial for beginning the analysis of this problem. The next step is to analyze Newton's second law on both objects M1 and M2. So I'll save our result here, I'll erase what we don't need, and then continue the analysis. So returning to our analysis of a pulley with two masses and a string that's not slipping around the pulley, I now want to begin analysis of F equals NA on object 1. So as usual, I draw object 1. I'll choose I hat 1 to point in the direction because I know it's going to go that way, so my component acceleration will be positive. And my force diagrams, I have a normal force, I have gravity. The string is pulling T1, that's the same tension at the end of the string. The tension in the string is not changing, we're assuming it's a massless string, and I have a friction force on object 1, which is kinetic friction. And now I can write down Newton's second law in the horizontal direction. I could also call J hat 1 up. And my two equations for Newton's second law is T1 minus Fk is M1A1, and N1 minus M1G is 0. Now, I also know that the kinetic friction, Fk, is the coefficient of friction mu times N1. So my next equation for F equals Ma on object T1 is T1 minus mu N1 equals N1A1. Now I have to apply the same analysis to 2. Notice I'm not drawing my force diagram on my sketch. I do a separate force diagram on 2. So here's 2. I have tension T2 and gravity M2G. Now, even though I chose a unit vector up here, this choice of unit vectors is completely independent of how I choose unit vectors for 2. Because object is moving down, I would prefer to choose J hat 2 down. My acceleration for this object will be positive. And then when I apply F equals NA to object 2, I get M2G minus T2 equals M2A2. So that's now my third equation, that M2G minus T2 equals M2A2. And now I look at the system of equations, and I have, what are my unknowns? T1, T2, alpha, A1, A2, 5 unknowns. I'm treating properties of the system, the radius, mu, ICM. Actually, the N1, because it's M1G, I can simplify this equation and replace this with M1G, where I'm already using the other Newton's second law. So I have 5 equations, I have 3 equations and 5 unknowns. I cannot solve this system. But in all of these problems, there's constraint conditions. There's constraints between how the masses are moving and how the angular acceleration of the pulley is related to the linear acceleration of masses. Let's consider mass 1 and 2. They're attached by a string. As mass 2 goes down, mass 1 goes to the right. The string is not stretching, so they're moving at the same rate, so they have the same acceleration. So my first constraint is that A1 equals A2. Now in general, I have to be careful, plus or minus. Why is it a plus sign and not a minus sign here? It's a plus sign because I've chosen I hat to the right and I've chosen J hat to downwards. If I'd chosen them differently, that sign could have varied. Now let's focus on the relationship between the angular acceleration of the pulley and M2. Think about the string. Here, we're on a point on the rim. This is a distance r. And the string, the pulley and the string are moving together. So there's a tangential acceleration of the pulley equal to r alpha z. This is the tangential acceleration of pulley and string. But the same string has a linear acceleration, either a1 or a2, so this has to be equal to a2. This is a linear acceleration of the string. And so that's our last constraint, 5, that a1 equals r alpha. And now I have a system of 5 equations and 5 unknowns, and the question is how can I find the acceleration? So in general, when opposed to a system like that, I want to have some strategy. Let's make a little space to clear for our algebra. Okay, now, I look at this system, and I say to myself, which equation do I want to use as a background? My target is to find a1. a1 is equal to a2. Now, when I look at these equations, T1 depends on A1, T2 depends on A2, which is equal to A1, and alpha is also related to A1. So I can use this equation 1 as my backbone and substitute in T1, T2, and alpha into that equation. And now let's do that. So when I solve this equation for T1 equal to m1a1 plus mu m1g with a minus sign, I get minus m1a1 plus mu m1g times r. That's my first piece. I solve for T2, which is m2g minus m2a. So I get m2g minus m2. Now a2 is equal to a1, so I make my second substitution, multiplied by r, and that's equal to ICM. And now I make my final substitution, that alpha z is equal to a1 over r. So if I now can collect terms, minus, minus over here, but there's an r there, and r there, I'll divide through by r, and bring my a1 terms over to the other side, and I'm left with minus mu m1g plus m2g equals ICM over r squared. That has the dimensions of mass, because moment of inertia m r squared divided by r squared, plus m1 a1 plus m2 a1. And finally, as a conclusion, I now can solve for the acceleration of my system in terms of all of these quantities, and let's just put it all the way down here at the bottom, that a1 equals m2g minus mu m1g over ICM r squared plus m1 plus m2. Often in types of problems like these, when there's a lot of sign errors, you might end up with a minus or a minus sign down here. And if you look at that, that would imply that with the right choice of parameters, this could be 0, and that would be an impossible solution. So that's always a sign that there could be something wrong. The other thing we want to check is, when does it actually accelerate? We have a condition. So we can conclude that if m2g is bigger than mu m1g, then 2 will start to go downwards. If m2g were less than m1g, then the problem would be very different, because 2 would not go downwards. The friction would not be kinetic, but would be static, and that would vary depending on how much weight were here. So if you went from 0 to mu m1g, the static friction would depend on how much weight that's there. So here is a full analysis of rotational and translational motion. It takes a little bit of time and a little bit of care, but we've done it.
Good job.
We recently introduced a vector quantity called torque, a sort of rotational analog to force, and we saw that an applied torque changes the angular motion of a rotating body in just the same way that an applied force changes the linear motion of a translating body. This week, we are going to introduce the concept of angular momentum, which relates to torque and rotational motion in the same way that ordinary momentum relates to force and translational motion. Like torque, angular momentum is defined in terms of a cross product or vector product. Specifically, the angular momentum vector L for a point mass is equal to the cross product r cross p, where r is the position vector measured from a chosen reference point, and p is the ordinary momentum vector. We will also encounter a third conservation principle, this time for angular momentum. An applied torque causes the angular momentum to change. However, if there are no external torques on a system, then the angular momentum of the system is conserved or remains constant. This is a powerful tool for solving many problems. One subtlety is that angular momentum, like torque, is defined relative to a specified point. So for a given system, the angular momentum with respect to one point might be conserved, while the angular momentum with respect to a different point might be changing. Often, in analyzing a system, we must be careful about our choice of reference point for torques and angular momentum in order to take full advantage of the conservation principle. Angular momentum is a particularly subtle and non-intuitive concept in comparison to momentum and energy, and the resulting motion is often surprising. It is worthy of particularly careful study.
Okay.
We will now introduce a new kinematic quantity called angular momentum. Angular momentum will be very useful when we describe the rotation of objects, in particular, how it will be related to torque. Now, what is angular momentum? Suppose we have an object of mass m, and it's moving in this direction, and it has momentum p. Remember, p equals mv. Angular momentum is always defined about some point. So suppose we choose a point s, and I want to define the angular momentum about s due to this motion of the object. And the way it's defined is I'll draw a vector from the point s to where the object is, and our definition of angular momentum about s is equal, this is 3 lines for our definition, it's the vector cross product of the vector rs with the vector p. Now, how do we define the direction of this vector? Well, the way we do that for any vector product is we take the two vectors and we put them tail to tail. So let's start off by drawing the vector rs in that direction. And now when you take the cross product, we draw an arrow from the first vector to the second one. Remember, crossing vector products are the same thing. And now we want to use our right-hand rule to get the direction of the angular momentum. So we curl our fingers, and notice in this case it's pointing into the plane of the figure. And so the direction of the angular momentum about s is given into the plane of the figure in our lightboard. Now, we'll learn how to calculate this cross product in detail, but suppose we have our vectors which are in a slightly different arrangement as seen in this figure here. Well, what we see is that the vector p and the vector rs, we still use our right-hand rule to calculate the direction of ls. Notice whenever you have a vector cross product, that the vector ls is perpendicular to both the vectors rs and is perpendicular to the vector p. And you can see in both of these examples that the angular momentum is perpendicular to the plane formed by the vectors rs and p.
Here we will talk about the calculation of angular momentum. People often forget that angular momentum can be calculated for any object, even for an object that's traveling in a straight line and not rotating at all. For example, here I have an object with mass m moving at a speed v along a straight line. Another important thing to keep in mind is that angular momentum does not have a definite value. It depends on the choice of origin, which is arbitrary, although some choices are easier to calculate or more useful than others. Here, I will choose this completely random point to be my origin. Notice that it can be any point in space. Angular momentum is a lot like torque. They both involve a cross product of a distance vector with another vector. For angular momentum, it's the distance vector r, the vector from the origin to the object, cross p, the momentum of the object, or mv. Once again, we can write the magnitude of this cross product as r times mv times the sine of the theta between the two. But it's often more helpful to think about this as r times sine theta times mv. In other words, the r sine theta is the component of the position vector that's perpendicular to the direction of the momentum. Let's practice with a few other examples. If I have a ball moving up, and I have my origin at the side, then this is the perpendicular distance. So the angular momentum is r perpendicular times mv. A reference point that's the same horizontal distance away from the object will see the same angular momentum. Notice that in this case, the angular momentum is not changing as the ball moves because the perpendicular distance is not changing with time. In this case, if the ball is moving at an angle, we again have to take the perpendicular component of the position vector to find the angular momentum. This second reference point is now a different distance away, so the angular momentum is larger. Now let's talk about the sign of angular momentum. You can calculate the sign of a cross product with the right-hand rule. Make sure your vectors are tail to tail when you compare the directions. So in this case, we have that r cross v points into the page. In the case of circular motion, r and v are always perpendicular, so we can just multiply the magnitudes together, and the sign tells us which way we're going around the circle. If we consider out of the page to be positive, and the angular momentum is positive, then the object is circulating counterclockwise. If the angular momentum is negative, the object is circulating clockwise.
I'd like to now calculate the angular momentum of a two-particle system. So here's one particle, call that 1, and here's the other particle 2. And particle 1 has a momentum in the downward direction, and particle 2 has a momentum in the upward direction. Now, in this case, I want to make the sum of the momentum, so this momentum of the system is 0. And now I want to calculate the angular momentum about two different points. So let's just draw an axis here, and let's choose one point A, and we'll call this distance r, and this distance r, and let's choose another point B, and we'll call that distance d. Now, in order to calculate angular momentum of the system, I need to draw my vectors. Let's start with the angular momentum about the point A. That's going to be a vector from A to object 1, cross the momentum of 1, plus the vector from A to object 2, cross the momentum of 2. Now, what's crucial here is at this point, things are a little bit abstract, but we want to draw these vectors RA1 and RA2. So we're now constructing our angular momentum diagram. So there's RA1 and there's RA2. But again, in order to calculate this, we could do it geometrically with right-hand rules, but I now want to introduce unit vectors so I can do vector decomposition at every point. So I'm going to choose a unit vector I hat, j hat, and k hat. And now I can decompose all of these vectors in terms of my unit vectors. This is the angular momentum of the system. So now it's not hard at all to write these out. RA1 is minus r in the I hat direction. Cross P1 is down. That's minus P1 in the j hat direction, where P1 is the magnitude. And RA2 is in the plus I hat direction, so that's r I hat. And I'm crossing that with P2, which I'll write right now as P2 in the j hat direction. Now remember, P2 has the same magnitude as P1, but they're pointing in opposite directions. So when I take the cross product, I hat cross j hat is k hat, minus sign, so I get rp1 k hat. And now over here, P2 is equal to P1, I hat cross j hat is k hat, and I get another rp1 k hat. And so I have two rp1 k hat. And that's the angular momentum of the system about point A. Now I'd like to calculate the angular momentum about B. So let's draw the same diagram, 1, 2. Here's P2, here's P1, here's B. And now I'll draw my vectors. This is RB2, and this is RB1. This distance was 2r, this distance was d. I'm going to use the same unit vectors, and so I get L for the system about B. Again, I'll just write everything out. P1 plus RB2 cross P2. So I'm going to write P2 as, in this case, it's equal to minus P1, and magnitude P2 equals P1 in magnitude, directions are opposite. So RB1 is equal to 2r plus d I hat, and it's pointing in the minus I hat direction. Cross P1 is in the minus j hat direction. RB2 is also in the minus I hat direction, so that's minus d I hat. And P2 is in the plus j direction, so that is plus, the magnitudes are the same, P1 j hat, we don't need the plus sign there. And now I take the cross products. I hat cross j hat is k hat, a minus sign, that makes plus, so I have 2r plus d P1 k hat. Now notice here, I have I hat cross j hat, which is k hat, but there's a minus sign, so I have minus d P1 k hat. Here I have plus d P1 k hat, minus d1 p k hat, and so I get 2r P1 k hat, and I have the same result. L system A equals L system B. Now that's not a coincidence in this problem, and the reason is that whenever, so we can say it this way, whenever the momentum of the system is 0, then L, A, is independent of the choice of the point A. So coming back to our example, no matter where I picked our points, A and B, any point I could pick anywhere I want. I could pick a point C up there. I make this cross product calculation, I would get exactly the same answer, 2rp1k.
Okay.
But we've been calculating angular momentum about a point. Recall our definition of angular momentum. We've been looking at cases where the particle is moving linearly. Now let's look at a case where the particle is undergoing circular motion. So suppose we have a particle that's undergoing circular motion m. And let's choose some axes. And our particle, we can note that it's rotating about the vertical axis. I'm going to call that axis k hat, and I'll make that omega squared, omega z positive. So it's rotating about the k axis, the z axis. Now, when we calculate the angular momentum, we know because it's rotating about the z axis, this is our z axis, that the particle has a velocity tangential to the circle. So its momentum is tangential to the circle. And we draw our vector rs to where the object is. Now, what is it? You could solve this in Cartesian coordinates, but then you might have to do some vector decomposition. But because there's a central point to this motion, whenever there's a central point, we like to choose cylindrical coordinates. And the way we'll do that is we'll define some angle theta. If this were my plus x, my plus y axis, then that's consistent with k hat being up and our definition of omega. And I'll define an r hat unit vector, which is pointing radially outward from the center of the circle, and a theta hat vector, which is tangent to the circle. And now I can calculate, I can write down, say the radius of the circle is r, then L of s, the vector rs has radius r, pointing outward, and the momentum vector is pointing tangential. And that's a very easy cross product to make, r hat cross theta hat. That's what we're defining to be k hat, maintaining the cyclic order. And so we get r p k hat. Now, for circular motion, the momentum magnitude is m, the magnitude of the theta component. We've made that positive, which is mr omega z. And so ls is, there's an r here and another r there. So we get m r squared times omega z k hat. This is our vector omega. Now, this turns out to be the moment inertia of a point particle located at the center, and so we conclude that the angular momentum is proportional to the angular velocity. Now, that's no surprise in this particular case. Why? Because the vectors rs and p are in the plane of motion. And whenever you take a cross product, L is perpendicular to both of those vectors, so it's perpendicular to the plane of motion, and therefore L has to point in the z direction.
Let's look at the angular momentum of two particles, one sitting here and one over there. And they're circling each other. And we want to determine the angular momentum of a point on the ground right here underneath. That's our point S. And here's the center, so the circle has a radius r, and here we have a height h. And let's have the particles go counterclockwise, because then we can define our k hat vector to go up. And if these particles are going this way, then omega is also going to be going in the k hat direction, in the positive k hat direction. So we know that L equals r cross p. So we need to determine where's r and what's going on with p. So our r vector goes here from point S to our first particle, rs1. And here's number 2, and we have rs2 sitting over here. And p, the momentum of the particles, well, if these guys are going in the counterclockwise direction, then the momentum of particle 1 is going to go into the board following the direction of the motion. And here, p2 is going to come out of the board. If we consider this equation here, we can already graphically determine what the answer is actually going to be. And so we do r cross p, so r cross p, which means ls1 is going to point in this direction, ls1. And alternatively, ls2 is going to go this direction. Which means if we add these two components, and we do want the total angular momentum of the system of both particles, so we have to add them, we'll get here our L of the system. So in order to calculate that, we need to calculate first the ls1 and then the ls2, and then we need to add them. The crucial point here is to be careful with the coordinate system. For the first particle, k is going up, and r is going outwards, and theta hat is going into the board. Then we can write up ls1 equals r1 or s1 cross p1. And we can express this vector here with h and with r. So we have r in the r hat direction plus h in the k hat direction cross p. And p is the mass of the particle times the angular velocity, the component. That is r omega z, and that goes in the theta direction. So we need to solve this cross product here. We're going to have m r squared omega z, and then we have r hat cross theta hat, that's k hat, plus h m r omega z, and then we have k hat cross theta hat, that's anticyclic, and we get an r hat, and this is, by the way, an r1, and this is an r1, and we get a minus because it's anticyclic. So we're going to turn this here into a minus. And that is the momentum, the angular momentum for our first particle. Now we're going to do the same in an analogous way for our particle number 2, but again, we need to look at the coordinate system. That's very crucial here. So k hat still goes up. R hat now goes into the other direction, and accordingly, theta hat comes out of the board. And then we can just write down our ls2 here as the same thing, m r squared omega z k hat. And here we have minus h m r omega z r2 hat. And we know from our setup here that r1 equals minus r2 hat, r1 hat equals minus r2 hat, which means when we now put it all together, we want L equals ls1 plus ls2. We can tally this up, and from this we will see that the r hat term actually falls out, and we are left with 2 times the first term. So we have 2m r squared omega z k hat. And that's exactly what we wanted. We wanted an L pointing in the k hat direction. That's exactly this here. And what you can also see is that the 2m here is the mass, the total mass of the system, namely 2 particles. We could do the same exercise again for 4 points, because we'll add 2 here. Then we would get 4m here, so this is the mass of the system. And if we were to add many, many more points all along the rim here, we get to a solid ring, which means that either we know the total mass of the ring that we could stick in here, or we can integrate along the rim and then get to the total mass here, and we'll always get to the same kind of form.
We'd like to now calculate the angular momentum about an axis of rotation of a symmetric object like a ring. So here's our axis of rotation. We're going to have omega pointing up. That means omega z will be positive, because that's going to be our k hat axis. And this is a ring of mass m and radius r. So here's our radius. Now, and we're going to choose a point that lies somewhere on the symmetry axis of the ring, and the object is rotating about that symmetry axis, so it's passing through the center of mass. Now, the way we'll do this is we'll divide our ring up into pairs of symmetric objects. So we have an m here and a little delta m there. And we're going to calculate the angular momentum first of that pair. Well, we've already made that calculation, that the angular momentum about S of the pair is twice the mass of each object, that's the mass of the pair, times r squared, and it points in the omega direction. And so to get the angular momentum of the ring, we'll just sum up a set of symmetric pairs until we expand out over the entire ring. And so L of the ring about S is just the sum over the pairs of the mass of the pair times r squared omega. And r squared and omega are all constants. The total mass of the ring is just the sum over the pairs of the mass of the pair. And that's the total mass m of the ring. And so what we get is m r squared omega, L of the ring, S. This is the moment of inertia about the axis for the ring, because all the mass is distributed a distance r away. And so we see for a continuous symmetric body like a ring, again, because it's symmetric, the angular momentum only has a component along the axis of rotation. Now, what if we had an extended symmetric object? And let's see if I can possibly draw something like that. So we'll draw a pear-shaped object. What is the moment of inertia of this pear-shaped object, which is intended to be symmetric, about the z-axis? Well, I can think of that pear-shaped object as consisting of a ring, and it's a solid object. This is a solid symmetric object. And then inside the ring is just more rings. So the whole disk here is just a superposition of rings. And so the moment of inertia, so the angular momentum of just this disk is the moment of the disk about the axis. And now I'll just add more disks that are symmetric. And so by exactly the same calculation as I have here, the moment of this symmetric object is just, the moment of inertia is more complicated for this object, and it points in the omega direction. So again, in conclusion, a symmetric object about the axis of rotation only has a component of L pointing in the direction of omega. Constant of proportionality between the angular momentum and the angular velocity is the moment of inertia about that axis. This we need to calculate for each symmetric object. So now we'd like to consider systems in which the total momentum of the system is 0 and show that L, the angular momentum, is independent of the choice of point A. So let's consider this. Let's draw a picture here, and let's make our system a bunch of discrete particles, particle 1, particle 2, and let's call this the jth particle. And let's just choose a point A right here, and let's choose a point B right there. And I'll show that L for the system about A is going to be equal to L of the system about B. Now, in order to make an angular momentum diagram, we have the momentum Pj of this particle, and likewise for all the other particles. And I'll draw a vector Raj. Likewise for B, I'll draw the vector Rbj, and I'm also going to draw a vector from B to A. I'll make that capital. This vector is a constant because the points A and B here, A and B, are fixed points. Okay, now let's calculate the angular momentum about A for the system. It's the sum of J goes from 1 to n of the vector Raj cross Pj. And I can use the angular momentum of the system about B is J goes from 1 to n of Rbj cross Pj. Now I'll use the vector triangle that the vector from B to J is equal to the vector from B to A plus the vector from A to J. So we have that Rbj is equal to the vector from B to A plus the vector from A to J. And I'll substitute that into our expression for the angular momentum about B. So the angular momentum about B is the sum J goes from 1 to n of Rba plus Raj cross Pj. Now, the vector product distributes over vector addition, so this is two sums. So let's write them both out. J goes from 1 to n of Rba cross Pj plus the sum J goes from 1 to n of Raj cross Pj. Now already you're seeing that this term is the angular momentum of the system about A. This term is the interesting one. Rpa is a constant vector. No matter which particle I choose, 1, 2, the jth particle, this vector is always the same. So I can pull it out of the sum, and I get Rba cross product, the sum of J goes from 1 to n of Pj. Now we've already recognized this term as the angular momentum of the system about
Yes.
A, and this is just the total momentum of the system. So we have equal to Rba cross the total momentum of the system plus the angular momentum of the system about A. And that's the angular momentum of the system about B. So this is our general result about how angular momentum differ between 2 points. But now, if P system equals to 0, the first term is 0, then L of the system about B is equal to L of the system about A. And we've proved our proposition that if the total momentum of the system is 0, then the angular momentum doesn't depend on the point we choose. Now, what's interesting here is that the reference frame moving with the center of mass, by definition, has P in that frame, let's call it the system, and this is the Cm frame, is 0 by definition. So this is one more reason why the center of mass reference frame is an important reference frame. Because in the center of mass reference frame, the total momentum by definition is 0, and therefore the angular momentum is independent of any point that you choose in that reference frame. And so we can say that the system, when we talk about a system's angular momentum, we're referring to the angular momentum in the center of mass reference frame.
Great.
Let's consider the motion of a symmetric object that's rotating about a fixed axis. So we could take some object, and we can imagine this is sort of what sometimes people refer to as a spinning top, and it's rotating about this symmetry axis k. And we know that the angular velocity of the object we can write as omega z k hat, and the angular momentum about this symmetry axis we just showed that was equal to the moment of inertia about this axis times the angular velocity. And in particular, the magnitude of the angular momentum, and I'll just write that L about that axis, is I axis times the magnitude of the angular velocity. Now we've seen separately that the kinetic energy about this axis, which we'll call the rotational kinetic energy, was 1/2 times the moment of inertia about that axis times the angular velocity squared. But here we see that omega squared is equal to L over I. So if we substitute that in, we get L squared about that axis over I axis squared. And so we have a nice expression for the rotational kinetic energy is L squared about that axis over 2 moment of inertia about that axis. And this we can describe as the kinetic energy of a symmetric body about a fixed axis. It is nice to notice the linear analogy to this when we wrote that the momentum of an object was mv. So the magnitude of the momentum is just m times v. And when we write kinetic energy, translation, as 1/2 mv squared, we can write that as the translational kinetic energy as p squared over 2m. So once again, we see this nice analogy for rotational motion, where we describe it in terms of the angular momentum and the moment of inertia, and the linear motion we describe it in terms of the momentum and the mass. When we analyze a single particle motion, say we have an object which is moving with momentum p, then we have two principles. Our Newton's second law told us that the force on the object causes the momentum to change. And now what we'd like to do is consider another principle. Suppose we're looking at some point about s. We'd like to show that the torque about s is equal to the change in angular momentum of the particle about s. So let's now investigate that. Well, recall that angular momentum is defined to be about a point, a vector s, and we'll indicate m to show that this is the vector from s to where the object is located across the momentum of the object. And what we want to now calculate is the time derivative of that quantity. Well, when you take the time derivative of a vector product, it's the product rule, and so there's two terms here. It's drs m dt cross p plus rsm cross dp dt. Now, no matter what the point s is, the derivative of the vector that's measuring where s to the mass is always the velocity of the object. So that's the velocity, and momentum is just mass times the velocity. And you can see that that quantity is zero because a vector direct product with its cross product with itself is zero. And this second term, notice that we have dp dt in here, and it's always crucial to understand in these calculations where the second law comes in. This is just rsm cross f. And recall that when we talk about the torque on an object about the point s by the action of, say, some force, and so suppose we had a force acting on this object, and that's going to cause the object to change its direction by some amount, delta p, then the torque by definition is rsm cross the force, and we see that that is exactly equal to the change in angular momentum. And so for a single particle, the torque about a point s causes the angular momentum about that point to change. And this result will generalize for a collection of particles in a calculation that's very simple. Let's now consider the generalization of the result that the torque on a single particle about a point causes the angular momentum of that particle about that point to change to a collection of particles. So let's begin by indicating some ith particle with momentum pi and some jth particle over here with momentum pj. And this is a big system of n particles. And we'd like to calculate the angular momentum about some point s. So that angular momentum will consist of the direct product of the vector from s to the ith particle and the direct product of the vector rs to the jth particle. So the angular momentum total will be the sum over all the particles 1 to n of this sum rsj cross pj. Now, what we'd like to do is, again, as before, take the time derivative of this angular momentum. We have the sum, j goes from 1 to n. We have two derivatives here by the product rule, cross pj, plus the sum, j goes from 1 to n, of rsj cross fj, where we use the fact, as we did before, that the force on the jth particle is equal to the change in momentum of the jth particle. Now, this first piece, again, the derivative of the vector from s to the jth part is the velocity. So we have j equals 1 to n of v, the velocity of the jth particle, cross mj vj, and that's 0. As we know that a vector cross product with itself is 0. And this piece in here, now we have to be a little bit careful, but rsj cross fj is the torque on the jth particle. So that is the torque on the jth particle. Now, remember that we showed that the forces on the jth particle could be both due to internal or external forces, and as long as the internal forces pointed between two particles, pointed along the line connecting those particles, the internal torques cancel in pairs, and this will only be the external torque. So we've assumed that the internal torques cancel in pair, and that has to do with an assumption about the direction of the internal forces, and so we can conclude that this is just the total external torque about the point s total, and we'll drop that total, and we'll conclude that the torque for a system of particles causes the angular momentum of the system of particles to change. The calculation is exactly like a single particle, with a few subtleties that have to do with internal torques canceling in pairs. Let's consider the motion of a single particle moving with a velocity d in a ground reference frame, say. Recall that we defined the momentum of this object as mv, and we know that Newton's second law can be written in terms of the change of momentum, dp dt. And when we integrated Newton's second law for impulse, causes the integral of dp from some time t prime equals 0 to some time t, so we're integrating t prime. And here, we're taking our momentum from some initial momentum to some momentum at time t. We have that the impulse causes the momentum of this single particle to change. And in particular, this is what we call impulse. And if the impulse is 0, so as an example, if the impulse f dt prime equals 0, that tells us that the momentum of our particle has not changed. Now let's consider our same thing for angular momentum. The only difference is that we choose some point s, and we'll write the vector rs to where the object is. And our angular momentum, we defined about the point s, was the vector from s, and we can indicate maybe to the mass m. So it's a vector from s to where the object is located, cross the momentum of the object. And this is how we define the angular momentum. And recall that our basic concept is that the torque about s causes the angular momentum about s to change for this single particle. Now, torque is if there's a force acting on the particle. So for instance, if the force were acting at some angle, not only does the force cause the momentum to change, but we know that if there's a torque about s, it will cause the angular momentum of the particle to change too. Now, let's talk about the angular impulse, which is integrating the torque from, say, sometime t prime equals 0 to sometime t, and that's the integral of the angular momentum about s. And now we're integrating this from some initial angular momentum to some final angular momentum, and just as before, we have that the angular impulse will result in a change of angular momentum. And in particular, if our angular impulse is 0, that implies that the angular momentum of this particle is constant. And so you can see the analogies. The important fact to realize is that in the reference frame, momentum does not depend on any point, but our angular momentum does depend on the choice of the point S. And in particular, in terms of the impulse, the torque about S is also a quantity that depends on S. And so that's the analogy between momentum of a single particle and angular momentum of a single particle. Let's consider examples of our principle that the external torque about a point S causes the angular momentum of a system to change about S. We've examined central force problems in which we chose the point S to be the central point, in which there was no torque. Now, as examples, let's look at a case where we have a pivoted object. So I could take an example of a object. Let's see, this will be an overhead view of a ring of radius r. And I'm going to have a mass coming in. I'll call this ring mass m1, this object m2. This object is coming in with initial velocity, and this is my pivot point. Now, when the object m2 is hitting the ring, we have a force F2 on 1. This is the collision. Here's our pivot point. And when this hits the ring, we'll have some type of pivot force. I'm just going to denote the pivot force. We're not quite sure what it will point at, but I'll just say F pivot for the moment is holding this point in place. At the same time, the object will have a force F12 acting on the object. Here's our pivot point P. And now, what point should we choose to see if there's no torque about? Suppose we choose the pivot point. Well, P. Well, clearly, the pivot force has no torque about the pivot because the vector from the pivot point to where the pivot force is acting is 0. Remember, pivot forces have no torque about the pivot point. However, this collision force will produce a torque about the pivot, and that's the angular momentum of the ring is not constant because the ring will start to rotate. Similarly, this object is will reverse directions or will do something due to the collision, and again, this force will produce a torque that's equal and opposite to the torque on the ring. This is the torque on the particle. But if we make our system equal to the particle and the ring, so we'll call this, our system is now both the particle and the ring, then these torques are internal, and because they're equal and opposite forces, the RS vector is exactly the same RS vector. The internal torques cancel in pairs. The pivot force produces no torque. So the torque on the system about the pivot is 0, and that tells us that the angular momentum of the system about that pivot point initially will be equal to the angular momentum about that pivot point finally, if we take two initial and final states. In particular, suppose our initial state is, here's the pivot. Our object is coming in. That was m2 vi. The moment arm is r. And our vector from here to the object, rs initial, has a moment component that way. If we put these vectors tail to tail and figure out that the angular momentum is pointing in this direction, L initial I, and the moment arm is r, then the initial angular momentum about this pivot point is just due to this moving object, so that's m2 vi, and the moment arm is r, and we'll denote its direction that way. Now, the final angular momentum, let's imagine that it sticks. So we have m2, pivot, and now our ring is going to be rotating with some omega final because this object hits it. And notice that this object is a distance root 2r from the pivot point. So the final angular momentum can be two different pieces. You can think of this as a system where we have I of the system about p times omega final, because now it's just a rigid body. And the angular momentum of the system is consisting of two pieces. It's the angular momentum of the ring about the pivot, plus the angular momentum of the particle about the pivot, times omega final. Now, this is the center of mass. This is the pivot point P. The angular momentum of the ring is the angular momentum about the center, we'll use the parallel axis theorem, angular momentum about the center of mass, plus the distance from the center of mass to the parallel axis, which is a distance r. So the first piece is ICM ring plus m r squared. And the angular momentum of the particle, this is going in a circle of radius r2, root 2r, so when we square that, by the way, this was mass of the ring was 1, mass of the particle was m2 times r squared, which is this distance squared, which is 2r squared times omega final. The moment of inertia of the ring is m1 r squared, about the center of mass. We have a factor 2, we have another factor of 2, and so we get m1 plus m2 times a factor 2 r squared omega final, which we can call omega f pointing out of the board. And so now we have an angular momentum condition, which is that m2 vi r equals 2 m1 plus m2 r squared omega final. And that is the statement that the initial angular momentum of our system, the ring is at rest here, is equal to the final angular momentum of the system, where m2 is stuck to the ring and they're all rotating about this pivot point with omega final. That's the angular momentum of the system about p, omega final. This is the initial angular momentum. And so I can conclude that omega final is m2 vi over 2 m1 plus m2 times r.
We have previously studied the translational motion of rigid bodies by analyzing the motion of their center of mass. We have also studied the rotation of rigid bodies about a fixed axis. This week, we will consider more complicated examples of rigid body motion, where translation and rotation are both occurring simultaneously. One example is if I toss a rigid body through the air, but give it a spin at the same time, so that it tumbles in space as it falls. A second example is a wheel that is rolling along a flat surface. Its location is translating, but at the same time, it is also spinning about its axis. A natural way to analyze such motions is to once again take advantage of Schall's theorem, which states that one possible way of describing the general motion of a rigid body is by a translation of its center of mass plus a rotation about its center of mass. This separation of the general case into two distinct types of motions will greatly simplify our analysis. One of the most common examples of simultaneous translational and rotational motion is that of rolling objects, and we will concentrate on this particular application. We will see that an important detail is whether or not the object rolls without slipping, and the role that friction can play in each case. The special case of rolling without slipping amounts to a constraint condition that relates the translational speed of the center of mass to the radius and the rotational angular velocity.
Let's consider a wheel that's rolling. So our wheel is rolling along the surface. The wheel has radius r, and I want to consider the motion of a point P on the rim of the wheel. Now, I'll choose an origin that's fixed. And in fact, here we're going to talk about the reference frame A, which is fixed to the ground. And I would like to consider, my problem is to find both the position of the point on the rim, the velocity of the point on the rim, and the acceleration of the point on the rim as a function of time. Now, the position vector is given from my fixed origin to where the point on the rim is. Now, this can be quite complicated, but what we're going to do is consider a second reference frame that is located at the center of mass of the wheel. So our second frame, we'll take reference frame, and we'll call this frame CM, is moving with the center of mass of the wheel. So in that reference frame, we'll denote this point by vector r, cm, because we're in the reference frame with respect to the center of mass, and we're talking about the point P. Now, these vectors are connected, and we'll call this vector capital R by our vector triangle, capital R equals the little rp, that's the position vector in the fixed frame of the ground, is given by capital R plus rcmp. Now, as we've seen before, by differentiating, the velocity of the particle is given by v plus vcmp. This one is the velocity in frame fixed to the ground. This is the velocity of the center of mass with respect to ground frame. And finally, vcmp is the velocity in the center of mass frame. Now, in order to analyze this law, what we'll now do is focus on what the motion looks like if you're an observer moving with the center of mass. And that's how we'll begin our analysis. When we discussed the rolling of the wheel, we chose a reference frame fixed to the ground. So that was our what we called frame A. And in that reference frame, the motion of the point P on the rim was quite complicated. Now what we'd like to look at it in the reference frame moving with the center of mass. And we call that frame CM. Now, the picture there is much easier because the object is in that reference frame, the center of mass is not moving, and the point P on the rim, the object is just undergoing circular motion. So in that frame, the velocity of that point P in the center of mass frame is just tangent to the circle, and as the object moves around, at a later time, the velocity is always tangential. And in this reference frame, it's just pure circular motion, and we know that the speed in that reference frame is given by the radius of the wheel times the rate d theta dt, and here let's define the variable theta this way. And so in this frame, what's happening is pure circular motion. Now we know our law of addition of velocity tells us that the velocity in the frame fixed to the ground of that point is equal to the velocity of the center of mass plus the velocity of the object, the point on the rim, in the center of mass frame. Now, what we want to do now is draw a picture which illustrates this law of addition of velocities. So now what we'd like to do is try to understand how to apply the law of addition of velocities so we can express the velocity of the point on the rim in the reference frame fixed to the ground. Now, the important thing to realize is v is the velocity of the center of mass of the wheel with respect to the ground, and every single point on the wheel has that same velocity v. So let's draw a picture of our wheel. Here we're in the ground reference frame. And let's first draw 4 points on the wheel and draw this velocity v. Every single one of these points has the same velocity v, 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 and v. Now, let's add to that the velocity of a point of the rim as seen in the reference frame moving with the center of mass. We just saw that every single point on the wheel is undergoing circular motion in that reference frame. So now let's draw those velocities. I'll just draw it right below, vcmp, down here, vcmp. Notice here it's in the opposite direction, vcmp, and up here it's pointing up. So when we add these two vectors together, what we get is a longer vector in this direction. It would be the sum of these two pieces. So we point like that. That's vp. Over here, it's the vector decomposition. So it's in that direction here. It's a shorter vector, vp. And over here, it's the vector sum, vp. So now what we've been able to do is describe the velocity of the point P as a combination, the vector addition, of how the center of mass of the wheel is moving and the circular motion as seen in a reference frame moving with the center of mass. Now what we want to explore is special conditions, which we'll refer to as rolling without slipping, slipping, or sliding. Let's now consider our rolling wheel. We want to look at some special conditions. So at time t equals 0, and we'll have our wheel that's rolling. Here's the ground. Let's say that our point P is right up here at the top. That's CM, and we'll be in the ground frame now. And then at a later time t, the wheel has moved to the right. So let's draw the wheel over here. The greatest picture of the wheel, but we'll have the wheel over here. And now the point P has moved some angle delta theta, and we'll call this time interval delta t. Now the center of mass of the wheel has moved a distance x cm is the velocity of the center of mass times delta t. And the point P on the rim, this arc change, this length here on the rim that P has moved around in the center of mass frame is r delta theta. Now, we want to ask ourselves, we'll call this delta x. We now have three possible conditions. We call rolling without slipping. That will be our first case, 1. And that's the case when the arc length, delta s, is exactly equal to the distance along the ground. So we have delta x cm is delta s. And so we get v cm delta t equals r delta theta, or v cm equals r delta theta over delta t. Now, in a limit, as delta t goes to 0, we have that delta theta over delta t in this limit, as delta t goes to 0, is d theta dt, and that's what we call the angular speed. So in our limit, as this wheel is rolling without slipping, we have the condition that the velocity v cm equals r omega. So that's our first condition, and we call this the rolling without slipping. Now, what is v cm? That's the velocity of the center of mass of the wheel, and every single point on this wheel has that same speed. And r omega, you can think of that as the tangential velocity in reference frame cm. This is just the speed in the reference frame moving with the center of mass. So this is our condition for rolling without slipping. Now, if the wheel, our second case is, imagine that the wheel is not moving forward at all, but it's just spinning. That's what we call the wheel is slipping on the ground, for instance, if there were ice. And so what we call slipping is a little bit more general. It's whenever the wheel is spinning and the arc length is much greater than the horizontal distance that the wheel is moved. So we have delta s representing the arc length that the point is moved in the center of mass frame is greater than how far the center of mass is moving. And so again, we have our delta theta is greater than v cm delta t, or in the limit, r omega is greater than v cm. You can say it's spinning faster than it's translating. And finally, the skidding condition. Skidding, imagine that the wheel, you're braking a wheel, the wheel is not spinning at all, but it's just sliding along horizontally, so the horizontal delta x center of mass is bigger than delta s cm. And so this is the case where delta x cm, how far it moved horizontally, is greater than the amount of arc length that that point moved. And so in the same type of argument, when we put our conditions in, we get that v cm is greater than r omega. And again, what that corresponds to in the skidding case, imagine the limit where it's not rotating at all, this would be 0, and it's just skidding along the ground, v cm. So we have our three conditions. We have the slipping condition where it's spinning faster than it's translating. We have the skidding condition where it's translating faster than it's spinning. And we have the rolling without slipping condition in which the arc length is exactly equal to the distance, horizontal distance along the ground.
Okay.
So I would like to now consider the wheel that is rolling without slipping. And what I'd like to do is consider, let's draw the wheel rolling without slipping. And I'd like to consider the contact point between the wheel and the ground. And I'd like to understand what the velocity of that contact point is, and the result is surprising. Now, we know by our law of addition of velocities, let's call that point P, that the velocity of P is the velocity of the center of mass, and that pointed this way, plus the velocity of the point P as seen in the center of mass frame. And in that frame, every single point on the rim was just doing circular motion, so that velocity is in the opposite direction. And the vector sum is the velocity of this point P as seen in the ground frame. So we want to consider the magnitudes of these two terms. The velocity in the center of mass frame of a point on the rim has magnitude equal to r omega. And we said that the velocity of just the center of mass, we call that v cm. Now the rolling without slipping condition was that these two magnitudes were equal. v cm equals r omega, or the velocity of the point on the rim in the center of mass frame is equal to the center of mass velocity of the wheel. And therefore, the velocity p, which is the sum of these two vectors, for the contact point, so that's when p is in contact with the ground, is equal to 0. So what we say is that the contact point is instantaneously at rest with respect to the ground. And that's what really is the mystery of a wheel that's rolling without slipping. That this contact point is the sum of these two vectors, and it's instantaneously at rest with the ground when the wheel is rolling without slipping. The other points are certainly not. Remember, up here, these two vectors pointed in the same direction, so that vector has twice the magnitude of either one. When a wheel is rolling without slipping, as we saw before, that the contact point here, the contact point is instantaneously at rest. Now, if the wheel is rolling on a surface with friction, then it's possible that we may have a static friction force. So there could be static friction may act. However, static friction always depends on the circumstances. Now, let's just consider two cases. Suppose here's a wheel, VCM. This is a horizontal surface. And in that case, the static friction, if the wheel is rolling with velocity v, in this case, F static is 0. And because of that, the wheel will roll without any friction, which is an idealization. There's other types of friction called rolling resistance, air resistance, etc., which will slow the wheel down. But in a perfect hard wheel, idealized wheel in a vacuum, it will keep on rolling. However, if a wheel is going down an inclined plane and it wants to maintain the rolling without slipping condition, so here we have VCM, and it has some angular speed, we have to be careful because in this case, if we differentiate, ACM is R alpha. So what is making the wheel spin faster? It has a non-zero angular acceleration. And if we look at the forces acting on the wheel, then we have a normal force, we have gravity acting at the center of mass, and we also have static friction. And it's precisely the static friction that is producing a torque about the center of mass. And that torque about the center of mass will produce an angular acceleration. So in order for the wheel to continue rolling without slipping, it must have both a linear acceleration, which comes from gravitational force component going down the inclined plane minus the friction, plus the alpha is coming from the torque. And so this side, if we wrote it as a vector equation, the torque about the center of mass would be the vector from, let's write this as RCM to where the static friction is acting. So that's the vector RCM, F static, cross F static. So in this case, F static is non-zero. So there are many circumstances in which static friction can vary between a zero value, some possible value, and some maximum value. And here we see one more example. In order for the wheel to continue to accelerate down the inclined plane and roll without slipping, that the static friction must produce a torque that causes the angular acceleration. And so we see that static friction depends on the other constraints in the problem. Now let's go back and analyze that same problem that we were looking at before of a wheel rolling down an inclined plane and it's rolling without slipping. But instead of using the energy method, we're now going to use the torque method. So let's consider the center of mass. And what we want to do is draw the forces. We have a normal force, we have gravity, and we have the friction force about the center of mass. Our wheel has a radius r. Let's choose a coordinate system I hat, j hat. And so we have a right-handed system k hat, and that will correspond to some angle theta. Now, here we're now going to enlarge how we apply both translation and rotation. And the beauty of this problem is we now can decompose our motion into translational motion and rotational motion. So for the translational motion, we'll apply Newton's second law. Now, if this is the angle phi, then that's the angle phi as well. And so our forces in the I hat direction, we have mg sine phi minus the friction force, and that's equal to the x component of the acceleration. Now, we also can choose the center of mass to calculate the torque. And so what we're really just studying here is simply our old problem in the center of mass frame of fixed axis rotation. And you can see gravity is acting at the center of mass, so it produces no torque about the center of mass. The normal force is directed towards the center of mass. And so when we take that vector product of r cross n from cm to this point down here, the contact point, these forces are anti-parallel, so the normal force produces no torque, and the only torque that we have is from the friction force, and that friction torque is going to give us a positive angular acceleration in the k hat direction. It's at right angles with the vector r, so we have Fs times r equals I center of mass times alpha. And these are our two dynamic equations. But remember, when the object is rolling without slipping, let's just remind ourselves that VCM equals R omega, and if I differentiate, the ACM, which is what we're calling AX, is equal to R alpha. So this AX here is the acceleration of the center of mass, and that's our third condition. And so now I see that I have three equations, and my unknowns, Fs, Ax, and alpha. And so I'm going to solve these equations for A. And I'll look at these equations, and what I'll do is I'll just substitute for alpha Ax over R, and then solve this equation for Fs and put it in there. And so I get mg sine phi. Now my Fs is equal to ICM over R times alpha, but alpha is Ax over R, so that's Ax and an R squared. Notice dimensionally, I is mr squared, so this is just ma, the dimensions of force, mg dimensions of force, and that's equal to max. And now I can solve for Ax. And I get mg sine phi divided by m plus ICM over R squared. Now, Ax is a constant, and we can, from our kinematic equations, if our object is moving a distance s as it drops a height h, we know from kinematics, and we could work this out, we have that the xcm is 1/2 acm t squared, and we know that, that the velocity vcm equals acm times t. And so when we put these two together, this is the distance s, we get that the velocity cm is equal to the square root of 2s times acm. Now s is equal to h over sine phi. H over s is sine phi. And so vcm equals the square root of 2 h sine phi times acm, but we've solved for acm, mg sine phi over m plus ICM over R squared. And so we get the square root of 2 mg h over m plus ICM divided by R squared. And this agrees with our energy method.
True.
I'd now like to consider a very unusual problem, and we saw a demo of this. Suppose you have a yo-yo, and the yo-yo has an inner radius v and an outer radius r, and the yo-yo is rolling without slipping along the ground. And what we have here is we're pulling the yo-yo with a string that's wrapped around the spool, and I want to find F max such that it rolls without slipping. If I don't pull it hard enough, the wheel will roll without slipping, and if I pull it harder, then this F max, the wheel will start to slip. So now let's analyze this problem, and let's use our dynamics approach. Let's choose an I hat, a j hat, k hat. As before, we'll define an angle theta, and now we'll apply both Newton's second law for linear motion and our torque about the center of mass. Now we have to consider our forces, so I'm going to put the forces on this diagram. We have the normal force from the ground pointing up, we have the gravitational force pointing down, and remember, it's rolling without slipping, so the contact point is instantaneously at rest, but because the center of mass of the wheel is accelerating, once again, in order to keep A equal to R alpha, then we need some type of torque that will produce a non-zero alpha, and that's going to come from a non-zero static friction. So once again, we have a case, unlike a wheel, which is just rolling along a horizontal plane, because we're pulling this yo-yo string, the static friction is not zero. Static friction depends on everything else that's happening in the system. And now we can apply Newton's second law, F equals ma. And so in our x direction, we have F minus F equals ma. And if we look at the torque about the center of mass is ICM alpha, then this is our x equation. Now here, both the pulling force and the static friction both exert torques about the center of mass. The static friction will exert a torque in the direction k hat, and the pulling force will exert a torque in the minus k hat direction. So our torques, the normal force does not produce any torque about the center of mass, nor does gravity. So what we have is Fs times the radius of the wheel, that is the torque due to static friction, minus B times the pulling force F, and that's equal to ICM alpha. So we have our two dynamic equations, and again, let's recopy our rolling without slipping condition now expressed in terms of acceleration. So now what I'd like to do is solve for this force F. And the way I'll do it is I'll write down from this condition alpha in terms of A over R. And from this equation, I have that, so alpha is A over R. And from the top equation, I have that A is F minus F static over mR times R. So I can replace the alpha in this equation, and I get Fs R minus Bf is ICM F minus Fs over mR. And now I just need to collect terms. I'll bring the static friction term to this side, and my F term to that side. And so I get Fs times R. And when I bring the static friction term over to the other side, I get ICM over mR. Let's just check dimensions. ICM is mR squared, so this terms have dimensions of length, so looks like I'm okay. And now I bring the F to the other side, and I get F times B plus ICM over mR. I can now solve for F, and I get F static, R plus ICM, m over R. It's a complicated answer, divided by B plus ICM divided by mR. Now, if I want to ask the question, what is the maximum force I can pull in which it just slips? What's physically happening is the harder I pull, the bigger the static friction is. I pull harder, static friction gets bigger. I pull harder, static friction gets bigger. But static friction can only have a maximum value. That hasn't changed. The maximum value of static friction is the coefficient of static friction times the normal force, which in this case is just normal balancing gravity, and g. So this is the maximum value that static friction can have. And so now I get F max, this is again a little complicated, US mg times R plus ICM divided by mR divided by B plus ICM divided by mR. And that is the maximum force that I can pull this yo-yo with, that it still rolls without slipping.
Is that it? No. Can't be it. Okay.
We already showed that the torque about a point can also be thought of as a decomposition. We take the vector from the point P to the center of mass and apply all the forces acting on the particle to the center of mass, and we can calculate the torque about the center of mass due to the action of some forces, where we're having forces acting about the center of mass. Now, if we choose the point P to equal the center of mass, then we know that the vector r center of mass to the center of mass is 0, so the torque about the center of mass is just equal to the forces about that point. We know that torque is always just LCM dt. Now, again, how could we justify that statement? That because we're only calculating the torque about the center of mass, it's only the rotational angular momentum about the center of mass that's changing. We saw before that if we thought of LP, again, as a translational and a rotational angular momentum, and the point P, rotational angular momentum, omega, and the point P was equal to the center of mass, then this first piece would be 0, and L about P is only ICM omega, and dLP dt is equal to ICM alpha for fixed axis, and that's exactly equal to dLCM dt. And so the point here is that when we're applying problems involving rotation and translation, we can just analyze the torque about the center of mass and only consider how the angular momentum about the center of mass is changing. And then for the center of mass motion, so this gives us our rotational dynamics, and for our linear dynamics, we will still apply F equals the total mass times ACM. So that's our linear dynamics. And this is our overall decomposition of rotational motion. To analyze it, we study the rotational dynamics and the linear dynamics.
Come on, you're in a player.
Let's consider the motion of a wheel that's rolling along the ground with some center of mass velocity vcm, and because the wheel is rotating, it has an angular velocity, and you can see that that vector is directed into the plane of the board. Now, what we'd like to do is consider the kinetic energy of this continuous body. A little bit later on, that body has moved some distance. And what we want to consider is the fact that not only is every point in the body moving with the center of mass speed, but there's this additional rotational energy that's associated with the fact that every point in the center of mass reference frame is undergoing circular motion. So how do we describe that? Well, we'll do that by choosing some point in the body. So let's pick a point. We'll call that mj, with mass nj. And the velocity of this point, remember, has two components. To simplify it, we'll give ourselves a little more picture here. The point has, every single point in the object has the vcm, but because this object is undergoing circular motion, there is vcmj. That's the rotational circular tangential velocity. And so the vector sum of these two is the actual velocity, vj, of the jth object. Vj is equal to the center of mass velocity plus the tangential rotational velocity that it has because it's undergoing circular motion. And now what we'd like to do is calculate the kinetic energy of this object. Well, the kinetic energy is the sum j from 1 to n of 1/2 mj times the velocity of this jth particle squared, which we can take as a dot product. So we can write that as vcm plus vcmj dot vcm plus vcmj. And that's just vj squared. So when we look at these terms, it looks complicated at first, but there's going to be vcm dot vcm, there's two cross terms, they're identical, and vcmj dot vcmj. So let's write out those three terms. We have 1/2 mj, vcm dot vcm is vcm squared. Now, every point in the object has the same vcm, so we can pull that one out of the sum. And now we'll take these cross terms, so we have the sum over j from 1 to n. There's two cross terms, so the 2's are going to cancel. And inside here we have to remember to keep our mass element. That's important. Now, I'm going to write it as mj, vcmj vector. Now, remember, when you dot with vcm, every single point has the same vcm. Every jth element has the same vn, so I can pull that vcm outside. And finally, I have the last term, which is the sum over j from 1 to n of 1/2 mj vcmj squared. And that's just the dot product of those two terms. And so our kinetic energy looks rather complicated. But let's focus on this term right here, because recall from our video on the center of mass that the definition of the center of mass reference frame, so if you're moving in the center of mass, that in the center of mass reference frame, the sum of mj vcmj is equal to 0. So, for instance, if you're in the center of mass frame, you're moving with vcm, the only velocity is this, and in that frame, the sum of mj vcmj is 0, and we did a video on that one before. And that's exactly what's in this term, so this term is 0. So this, remember, was how we defined the center of mass reference frame. And therefore, our kinetic energy consists of two pieces. This first piece is just 1/2 the total mass times vcm squared. And our second piece over here, we'll just write it out now, 1/2 sum over j mj vcmj squared. Now, if you were moving with the center of mass, then this jth object is just undergoing circular motion. And so we have our result that we've used many times is that the velocity, the tangential rotational velocity, is just equal to the radius, our sj. So let's introduce that, our sj, times the angular speed, omega. And when we put that into this term, we see our kinetic energy has two pieces, m total, v center of mass squared, plus 1/2, j goes from 1 to n, I didn't finish that sum there, mj, our sj squared. Now, just remember that every single point in the object has the same angular speed. And so we can pull out the omega squared in there. And because this is a continuous body, and we take the limit, as we've done before, as mj goes to 0, this quantity of mass times distance squared is just the moment of inertia about the center of mass of that body. And in conclusion, k is 1/2 m total, the center of mass squared, plus 1/2 the moment of inertia about the center of mass, times the angular speed squared. Now, this is the same crucial decomposition that we've talked about many times. This first piece is what we call the translational kinetic energy, because it just represents how the center of mass is moving. And the second piece is what we call the rotational kinetic energy, because it's a representation of just the kinetic energy of rotation. For example, if you were in the center of mass frame, there would be no translational energy, and this would be the only kinetic energy. Let's now consider how to find the velocity of the center of mass of a wheel that's rolling without slipping down an inclined plane. So let's draw a picture. Here's the wheel. It starts at t equals 0. And this is an angle phi. And at some later time t final, the wheel has dropped a distance h along the inclined plane. And now let's figure out what is the velocity of the center of mass of the wheel when it gets to the bottom. And we are now going to apply our energy arguments. Now, the first thing we have to realize is there's a very subtle point here, is that there can be friction. And we saw that when a wheel is rolling without slipping, there can be static friction at the contact point between the wheel and the ground. There's a gravitational force and a normal force. Now, static friction does no work, because the point is always instantaneously at rest, and f dot ds is 0 because the object is at rest. And so the ds is 0. So our static friction does no work, and therefore from our energy principle, that the external work equals E final minus E initial, we have no external work, and so our energy is constant. Now, how do we analyze our energy? Well, I've set things up, so I'm going to choose my potential energy to be 0 when it's at the bottom, and that our initial energy is only equal to potential energy. If the wheel has a mass m, gravitational force down, the potential energy initially is mgh. The final energy is only kinetic energy. The wheel is rolling with omega final. Its center of mass is moving with v center of mass final, and we just saw that the kinetic energy has two contributions. The translational kinetic energy, 1/2 m, we'll just call this final squared, and we'll make that v final just to make it easier, and it has the kinetic energy of rotation. Now, the rolling without slipping condition is that the translational center of mass v is equal to the radius of the wheel, r, times the angular speed, omega final. So I can write E final as 1/2 m plus ICM over r squared times v final squared, where I'm just replacing omega final equals v final over r. And therefore, that the kinetic energy, by the energy principle, tells us that E initial equals E final. So mgh equals 1/2 times m plus ICM over r squared, v final squared. So we can find that v final is equal to the square root of 2 mgh divided by m plus 1/2 cm r squared. And that is the final speed of the center of mass translational velocity of the wheel as it dropped a height h. We've already talked about kinetic energy for an object that's rotating and translating. Let's take again a simple object like a wheel, center of mass is moving, and we want to consider this is a bunch of point-like particles, a j particle of mass mj, and a position vector rcmj. And now what we'd like to do is, what is the angular momentum of this about some point p? And we're going to do the same type of decomposition that we've been doing right along. Let's draw the vector rj. This is the vector from point p to the object. Here's the vector capital R, and there's the vector rcmj. And our same vector addition, r plus rcmj. Now let's calculate the angular momentum about the point p. Now just let's recall two facts about the center of mass reference frame that we've already used. The first is that the sum of the velocities, the momentum in the center of mass reference frame is 0, and if you integrate this equation in just exactly the same way, if you added up the mass times each of the position vectors, that's mj, in the center of mass frame, that's also 0. So we've used this when we talked about kinetic energy. Now we're going to consider both of these results. So recall that angular momentum about a point is the sum of the vector from the point, cross product mj times the velocity vj. Now, we can also use our law of addition of velocities. Vj is v plus v cmj. And so now we're going to have to do both substitutions in here. That's why this calculation is a little bit more complicated. We have r plus rcmj cross mj times capital V. That is the velocity of the center of mass with respect to the ground frame, plus v cmj. Now, we have 4 terms in the cross product. And this time, we'll write them all out. So the first term is the sum over j of r cross mj capital V. The second term is, we'll take this one and we'll cross with that one. But because mj is just a scalar, I'm going to pull it in front. So that's mj, rcmj. And v is the same for every single particle in the object. Remember, v is just the velocity of one reference frame with respect to the other. So I can pull that out, cross v. And you're already noticing that this term will be 0. The next term is when I take r cross mj vj, v center of mass j summed over j. That's j, r, cross mj, vc, mj. But again, remember that r is the same vector. It's just from p to the center of mass. So I didn't need to put the sum here. I can pull r out of the sum, and I have my sum like that. And again, you're probably noticing that this term is 0, and our final term is rcmj cross mj vcmj. So our final term is sum r, rcmj cross mj vcmj. Now, from these two conditions, 1 and 2, both of these two terms are 0. And that's the power of using the center of mass reference frame. So LP, now let's look at the first term. Here, r is the same for every particle, v is the same for every particle. When we're summing over the mass, we're just getting the total mass. So the first piece is r cross m total v. And this last piece is precisely the definition of the angular momentum of the jth particle in the center of mass frame. So that's the sum over j of LCMJ, because RCM cross MVJ, R cross, say, whatever speed this is in the center of mass frame, it could be at some VCMJ, Vj minus capital V. This is exactly the angular momentum of that jth mass in the center of mass frame. And when we total all of this up, we have R cross M total V plus LCM. Now, what this first term is if you treated the whole object as a point mass, M total, moving with V, and here's our point P, and there's R, this is just what we call the translational angular momentum. It's treating the whole system as a point-like mass and just calculate moving with speed V, and that's just the angular momentum. We've called this V. And this piece is the angular momentum about center of mass. So sometimes we can think of the angular momentum as corresponding to a translational that has to do with the actual orbit of the object. You could call this orbital angular momentum. And this is the fact that the object is rotating. You could think of this as the spin angular momentum about the center of mass. This is the same type of decomposition that we saw with kinetic energy. There was a translational component of kinetic energy and a rotational component of kinetic energy. This is the analogous case for angular momentum about a point P.
Beautiful. Now come 3.
A pivoted rod held horizontal parallel to the ground and released from rest will simply fall, rotating about the pivot point. In particular, suppose we have a mass attached to one end of a pivoted rod. So here's my pivot, here's my pivoted rod, which we'll assume is massless, and it has a length d, and I attach a mass m to one end. If I let this go from rest, it will simply fall, rotating about the pivot point, which I'll call s. And it's easy to understand that in terms of the action of gravity, which is acting downward, and the resulting torque about point s. If I replace this point mass with a wheel of the same mass, so this disk is a wheel with, let's say, a radius r and the same mass m attached to a pivoted rod. The rod is massless and has length d. If I hold this horizontal parallel to the ground and release it from rest, it will still just fall to the ground. Not a surprising result. What is surprising is if I then spin up the wheel. So if I have the wheel rotating about its axle with some large angular velocity, little omega, and then I hold it horizontal parallel to the ground and release it from rest, then, remarkably, this wheel plus axle will not fall. It will remain horizontal parallel to the ground. But the center of mass of the wheel will execute a small circular orbit about the vertical axis through the pivot point. This remarkable and very non-intuitive motion is called precession, and the system that's undergoing precession is called a gyroscope. Let's see if we can understand this behavior in terms of the angular momentum of the system. So what I've drawn here is a side view of the system. So let's define some coordinates. So we have r hat in the radial outward direction, k hat in the direction of the z-axis, the vertical axis, and then we'll define theta hat pointing into the screen. Okay, so that's a side view. I'd like to now draw a top view. So let's say we're looking down along the z-axis from the top on the system. So now here's my pivot point, and here is a top view of my wheel. Okay? Again, this is a distance d. Now this is still the r hat direction. This is the theta hat direction, and the k hat direction is pointing out of the screen. Let's draw the forces acting on our diagram here. So the weight is acting at the center of mass of the wheel. That's mg downward, and there's a normal force acting upward at the pivot point. The torque is just given by r cross f, and so relative to point s, it's the distance d times the weight mg. So the torque is mgd, and by doing r cross f with the right-hand rule, we see that it's directed in the plus theta hat direction. Now, again, let's suppose that I'm holding the wheel horizontal and release it from rest. If the wheel is not spinning, okay, so this is not rotating, it's a stationary wheel, I'm holding horizontal, and I release it from rest, then its initial angular momentum with respect to point s is 0. Over a short time interval, delta t, the torque, which is acting in the theta hat direction, will cause an angular impulse, or a change in the angular momentum. That change in angular momentum, delta L vector, is equal to the torque times that short time interval, delta t, and it will act in the theta hat direction. The change in angular momentum will be in the theta hat direction because that's the direction that the torque is in. So for this case, and by the way, this view here, I should have labeled this is a top view. So this is the side view, this is the top view of the same system. So the torque is mgd in the theta hat direction. So in the side view, that's going into the screen, and in the top view, that's going pointing upward, the theta hat direction. So in the case where the wheel is not spinning, if we think about the top view, the initial angular momentum is 0, right? So I'll just draw that as a dot. So that's L initial equals 0. And then I add a small torque, or a small angular impulse due to the torque, delta L, which is in the theta hat direction. So that's pointing in the theta hat direction. Okay, so that's my delta L. And when I sum those together, I start out with 0, I add a small delta L, so my final angular momentum, a time delta t later, is just equal to my delta L. So this is L final, and that's pointing in the theta hat direction. So a torque in the theta hat direction into the screen for the side view is consistent with the wheel falling down. So with theta hat pointing into the screen, the wheel will basically fall this way. It's rotating about point s, and that's consistent with the torque pointing in the theta hat direction. Now, as the wheel falls, the torque continues to point in the theta hat direction until the angular acceleration will increase. Now, what happens if this wheel is not stationary, but instead is spinning rapidly? In that case, the torque remains the same. It's still mgd in the theta hat direction, but now the initial angular momentum is not 0. Rather, it is a very large vector pointing along the spin axis. Let's choose the sense of rotation such that L points in the plus r hat direction. That's actually the way I've drawn it here. So in that case, the angular momentum vector initially points in the plus r hat direction. So then what happens over a short time delta t? So now let's consider the case where the wheel is spinning. So now my initial angular momentum is a large vector pointing in the r hat direction. That's L initial. I'm adding a small perpendicular vector delta L in the theta hat direction. And so the sum of those two things, if this is the original r hat direction, what happened is that my new vector is at a small angle with respect to the original r hat direction. I'll call that angle delta theta. So what I've done is I've rotated my initial angular momentum vector by a small angle without changing its length. Okay? Notice the two very different situations. In one case, I start out with 0 angular momentum, and all the angular momentum I end up with comes from the angular impulse due to the torque. In the second case, where the wheel is spinning, I start out with a very large initial angular momentum. I then add a small angular impulse, small compared to my initial angular momentum, in a perpendicular direction. And that causes not a change in the length of the vector, but a change in its direction, which means that the angular momentum vector rotates. That's why the system precesses when the wheel is rotating rapidly. Before we can understand precession more carefully, it will be useful to review the mathematics of rotating vectors. So first, suppose we have a vector that I'll call r1, and I'm going to add a vector delta r to this, and I'm going to have the condition that the length of delta r is much, much smaller than the length of my original vector r1, and that delta r is much, much smaller than the length of my original vector r1, and that delta r is perpendicular to r1. So here's my delta r, And so if I add these two vectors, let's say R2 is the sum of R1 plus delta R, so that's my vector R2, and I'm going to call this angle delta theta. And now a few things to note. First of all, this is a right triangle, notice that the length R2 is equal to R1 divided by the cosine of delta theta. But if that angle is small, if delta theta is a small angle, then cosine theta is well approximated by 1, and so this is just my original length R1, and since R1 is equal to R2, I'm just going to call them both R, and this is for small delta theta. And so that tells us that the vector just rotates. When I have a large vector and I add a small perpendicular vector, the result is to rotate the original vector without changing its length. As long as the angle is small, or equivalently as long as delta R is very small compared to my original vector length, I'll get a pure rotation. In addition, again, looking at this triangle, notice that delta R is equal to, which I can describe as R, times the sine of delta theta. And again, if the angle is small, if delta theta is a small angle, then this is well approximated by R times the angle, delta theta, in radians. And again, this is for small delta theta. So now, if I divide this last equation by delta t, a small time interval in which this rotation is happening, then I write this as delta r vector divided by delta t, and I take the magnitude of that. That is equal to r delta theta divided by delta t. And if I go to the limit as delta t gets small, as delta t approaches 0, then I can write this as the derivative of the vector r, the time derivative, I should say the magnitude of the time derivative of vector r, and that's equal to the length r times the time derivative of the angle, d theta dt. But d theta dt is just the angular velocity, so I can write that as r times capital omega for the angular velocity. And this is just our familiar result that for circular motion, for the rotation of a position vector, the velocity is equal to the radius of the circle times the angular velocity of the rotation. Another way of thinking of that is that the magnitude of the rate of change of the position vector, which we call the velocity, is equal to the length of the rotating vector, r, times the angular velocity of the rotation. But there's nothing special about the position vector that I used in order to do this analysis. So if instead of a position vector, I considered any vector, so let's say this is my rotational motion of a vector that I'll call A. So that's A at time t, and then at some later time, that's A of t plus delta t. This vector is my delta A. I'll call this angle delta theta. And so the vector A is rotating in that direction with an angular velocity capital omega. Now, in the example I just did, my vector A is actually r of t. Okay? But so everywhere where I have an r here, I can just write an A. This is now just an arbitrary vector in space that is rotating at an angular velocity capital omega. And what we see using the same analysis, we would find that the magnitude of the time rate of change of the vector, that's the rotating vector, is equal to the length of the rotating vector, which is A, times d theta dt, or in other words, the length of the rotating vector times the angular velocity of the rotation. That's true for any vector. And this is a general result. V equals r omega is just a special case of this general rule, where in that case, my rotating vector is a position vector, but this is true for any vector that's rotating in space. In particular, for a rotating angular momentum vector, I have that the magnitude of the time derivative of the rotating angular momentum vector is just equal to the length of the angular momentum vector, the magnitude of the angular momentum, times the angular velocity of rotation. Now, in addition, in the particular case of a rotating angular momentum vector, or any angular momentum vector rather, we know that the time derivative of the angular momentum vector is also equal to the torque vector. So I can set these two things equal. In the case of a rotating angular momentum vector, the magnitude of the torque is given by the magnitude of the rotating angular momentum vector times the angular speed of rotation. And that's just using the general behavior of a rotating vector in space. Now that we've seen how to describe a rotating vector, we can use that to analyze the motion of our gyroscope. So again, I'll draw a side view of my pivot, my rod. Here's the wheel. I'll call this point S. That's the distance d. And we'll assume that the angular velocity is in that direction, so that the spin angular velocity vector is pointing outwards in the plus r hat direction. That's the k hat direction, and theta hat is into the screen. Now again, the weight is acting downwards at the center of mass of the wheel. There's a normal force acting upwards. So the spin angular momentum with respect to point S is just equal to the moment of inertia of the disk about its center of mass times the angular speed of the spin, and that's directed in the plus r hat direction. And this is the angular momentum with respect to point S. Now the torque with respect to point S, again, it's r cross F relative to point S. That's going to be mgd in the plus theta hat direction. And for a fast omega, omega is a large angular speed, and therefore if the angular momentum vector is a large vector, then the torque, which acts perpendicular to the angular momentum, will cause the angular momentum vector to rotate. And so as a rotating vector, we can write that the magnitude of the time derivative of that rotating vector is equal to the angular velocity of the rotation times the length of that vector. Okay? So the angular, and this is Ls. And so the length of that vector is just I times 1 omega, and then we multiply that by capital omega. Okay, now this quantity here, dl dt, is the torque. So that's the magnitude of the torque. But the torque we said is equal to mgd in the theta hat direction. And so the torque mgd is equal to I little omega times big omega. So I can solve for big omega. And big omega, which is the angular speed of rotation of the angular momentum vector, is mgd divided by the moment of inertia I times little omega. Now recall, little omega is the angular velocity, angular speed of the spin of the disk or the wheel. Capital omega is the angular speed of the rotation of the angular momentum vector. It basically tells us the speed at which the center of mass of the wheel orbits around the vertical axis through the pivot. We call capital omega the precessional angular velocity. So the precessional angular velocity is capital omega. And notice that the faster little omega is, the bigger little omega is, the slower the precession angular velocity is. Now, this expression tells us what the magnitude of capital omega is, what the magnitude of that precessional angular velocity is, but it doesn't tell us which way the system is precessing, whether, say, viewed from the top, the motion is clockwise or counterclockwise, or equivalently, which way the vector capital omega is pointing. We know it must point along the vertical axis, but does it point upwards in the plus k hat direction or downwards in the minus k hat direction? To see that, we need to look at which way the angular momentum vector is rotating. And there are two possibilities. So let's again go to a top view of our gyroscope. So suppose here's the pivot point, and here's my gyroscope, and the way I'm drawing things is that r hat is this way, this is the top view, so theta hat is that way, and k hat is out of the screen. So in the example that I did earlier, the angular momentum was pointing in the plus r hat direction, and so that's ls pointing that way. If the torque is pointing in the theta hat direction, then that's going to act to rotate the angular momentum vector this way. Okay? And so the sense of rotation will be like that. And so in that case, looking down on the system, we would see a counterclockwise rotation, and that's equivalent to omega vector pointing in the plus k hat direction. Alternatively, suppose the wheel were spinning in the other direction. And so the sense of rotation of this wheel around the axle were in the opposite direction. In that case, even when the wheel was on this side of the pivot, again, this is the top view, the angular momentum vector would be pointing in the opposite direction. So now this is my angular momentum vector pointing in the opposite direction that the axle is pointing. Still along a line, but in the minus r hat direction. But the torque would still be in the theta hat direction. And so my new angular momentum vector would rotate this way, which would be equivalent to the axle rotating in this direction. Okay? And that's equivalent to rotation in the opposite sense, clockwise as viewed downward from the top, or in other words, with capital omega vector pointing in the minus k hat direction. So the direction of precession depends upon which way the wheel is spinning, which way the spin angular momentum vector is actually pointing. Now, I'd just like to point out that there's an approximation that we've been making here. I've alluded to it, but I want to make it very specific right now. We have been assuming that the spin angular momentum vector L is large enough that the torque vector, which is perpendicular, provides only a small angular impulse that rotates L without changing any length. Okay? Now, as L rotates, the direction of r hat and the direction of theta rotate with it, and the torque is always in the theta hat direction. So after any small delta t, when the angular momentum vector rotates, the instantaneous torque at that next instant is still perpendicular to the rotating angular momentum vector. And so we're making an approximation that L is large enough that we can consider the instantaneous angular impulse as a small perpendicular perturbation. That's equivalent, it turns out, to saying that, so this is the approximation that we're making, that we've been making so far in this lecture, is that little omega, the spin angular velocity, is much, much larger than capital omega, the precession angular velocity. Okay? This is called the gyroscopic approximation. We'll see a more precise statement of it later on. But it's basically equivalent to saying that the spin angular momentum vector is so large that we can consider the angular impulse due to the torque as causing a pure rotation of the vector without any change in its length. It's important to keep in mind that a vector can include both a rotating component and a constant component. And in that case, it's important to identify what the rotating component is in order to use the analysis that we presented earlier. So for example, let's consider the case of a tilted gyroscope instead of one that's horizontal and parallel to the ground. So here's my pivot point. That's the vertical. And instead of a horizontal gyroscope, now I'll draw my gyroscope at some angle like this. Here's my wheel. I'll call that angle with the vertical phi. This distance is still d. And I'll use the usual coordinate system that r hat is pointing outward this way, k hat is pointing vertically, and theta hat is pointing into the screen. Now in this case, the gyroscope will still precess around the vertical axis to the pivot point, and the angle phi will remain constant. Now the angular momentum vector, due to spin, points now not in the r hat direction, but again outward along the axis of rotation. And that angular momentum vector can be decomposed into two components, an r hat component and a k hat component. So in other words, my angular momentum vector can be written as the sum of a vector pointing along the z-axis, or the k hat direction, plus a vector pointing in the radial direction. I could also write that as L sub z times k hat plus L sub r times r hat. Now notice, as this gyroscope precesses around, the z hat component is constant, but the r hat component rotates around. Okay, so the r hat component, the vector along the r hat direction, is a purely rotating vector, whereas the z component is a constant vector. Okay, so Lz is constant, and Lr is rotating. And so now, the magnitude of dl dt, which is equal to the magnitude of dlz dt plus dlr dt. Well, dlz dt, since that's a constant vector, is just 0. So the time derivative just involves the r component. And so that's equal to the angular speed of rotation times the length of the rotating vector, which is just the r component, not the z component. So this is multiplied by L sub r. Now in this particular case, the r component of the angular momentum vector is L, the angular momentum vector, times the sine of phi. So in this particular case, this would be omega times the full L
But that changes.
times the sine of phi.
if it-
So in the case that we have here, the angular momentum vector consists of a constant part and a rotating part. And the magnitude of the time derivative is equal to the angular velocity of rotation times the length of the rotating part of the vector.
Right, and the last video, congratulate me, 215 video.
Now we've been discussing
This is the last one for MIT 8.1 special class. Then we will do their examples. We will try to pass their exams. That's the next thing. And after that, we're off to a new subject, which will be either mathematics or thermodynamics.
steady, uniform precession, which is the simplest possible case of a phenomenon that can be much more complicated. As an example, in the case we've been discussing so far, where we release a gyroscope from rest when it's horizontal, very careful measurements would show that the initial motion isn't just steady precession, but has some additional motion superimposed on it. The spin axis sort of bounces or nods up and down as it precesses. However, friction at the pivot point causes the amplitude of the nodding to rapidly decay until it settles into steady precession. This nodding motion is called nutation. In our example, it decays so quickly that we don't even notice it. But if you had a perfectly frictionless pivot point, it would be a more noticeable effect, and it would persist for much longer. Now, there's an interesting point about our horizontal gyroscope that I'd like to point out. So here's my rod of length d, this is my point S. Here's my wheel that's rotating with some angular velocity. And again, there's the r hat direction, that's the direction that little omega vector is pointing in. That's the k hat direction. And that's the theta hat direction. Now, before I release the gyroscope from rest, the angular momentum vector points in the r hat direction as drawn at this instant. When I release it from rest, there is a torque acting in the theta hat direction that causes the angular momentum vector to rotate. And we've seen this in some detail. But there's something else to keep in mind, which is that now, when the system is precessing, that means that the center of mass of the wheel is orbiting around the z-axis, the vertical axis, through this pivot point. Okay? So you can think of that as a point mass with the full mass of the gyroscope moving in a circular path around point S with a radius d. That implies that there must be a component of angular momentum pointing in the k hat direction, pointing along the z-axis, corresponding to the translational motion of the center of mass, the circular translational motion of the center of mass of the gyroscope around the z-axis. But where did that k component come from? There was no initial z component of the angular momentum. We said that initially the angular momentum just pointed in the r hat direction. And there's no torque in the k hat direction. The only torque is in the theta hat direction. So how do we end up with some angular momentum pointing in the k hat direction? This seems to violate the conservation of angular momentum. The solution to this puzzle is that, in fact, the gyroscope doesn't remain precisely horizontal when I release it. Instead, it dips by a very small angle. So that's the horizontal. After I release it, the gyroscope's actually dipped downward by a small amount. I've exaggerated it considerably in this drawing. Call that angle delta theta. That small dip gives a small negative component of the spin angular momentum that's able to balance with plus z angular momentum due to the motion center of mass. Now, because the spin angular momentum vector has such a large magnitude, that's my spin angular momentum vector, only a small angle is necessary in order to get enough of a negative LZ component to balance out the LZ corresponding to the center of mass motion. Okay? But what we see is that, although gyroscopes seem like a remarkable system, they're not magic, and in fact, angular momentum is conserved. The faster little omega, the larger little omega is, the faster the spin angular velocity is, and therefore the larger the vector L is, the smaller that angle is, and the less of a dip that you get. So now we can write the exact angular momentum for the gyroscope. This is my distance d, this is my pivot point S. My spin angular velocity looks like that. Here's the r hat direction, the k hat direction, and the theta hat direction into the screen. And we're orbiting, the precession is around the z-axis with an angular speed, capital omega. Now recall that the total angular momentum with respect to point S can be written in two parts. There's the angular momentum due to the translational motion of the center of mass, and we know the center of mass is just orbiting around the z-axis, so I'll call that, in fact, the orbital angular momentum. So this is due to the translation of the center of mass with respect to point S. And then the second term is due to the rotational angular momentum, or spin angular momentum, relative to the center of mass. So this is due to rotation about the center of mass. So again, the general angular momentum of a rigid body is equal to the center of mass translational angular momentum plus the angular momentum due to rotation, a pure rotation about the center of mass. So let's write each of these terms. The orbital angular momentum, that is the translational angular momentum of the center of mass, is just due to the motion of the center of mass of the gyroscope, which is a radius d with respect to point S, moving in a circle with angular speed, capital omega. Okay, so that's equal to the mass times the center of mass velocity times the radius of the circle, and that angular momentum is in the k hat direction. But the center of mass velocity is just equal to, since it's a circular motion, is just equal to the radius of the circle, d, times the angular speed of the circular motion of the center of mass, which is capital omega. So I can write this as m capital omega d squared in the k hat direction. So that's the angular momentum due to the translational motion of the center of mass around point S, what I'm calling the orbital angular momentum. Now, the spin angular momentum, we've been talking about the rapid spin of the wheel around its axis. So that's given by the moment of inertia about that axis times the spin angular velocity, and that's pointing in the r hat direction. But there's a subtlety here. It turns out that is not the only rotation about the center of mass that this wheel is undergoing. And actually, because of that, I'm going to call this I1. And let me just draw a picture here. So for my disk rotating around this axis, the relevant moment of inertia is what I'll call I1. And for a disk, we know that would be 1/2 mr squared. The other rotation is a subtle one. Notice in this drawing, suppose I were to draw a dot on the outside face of the wheel. When this wheel processed around 180 degrees to the other side, that dot on the outside would be facing in the minus r hat direction now, or would be pointing to the left rather than to the right. And what that means is that this disk has actually rotated about its diameter. So this disk has rotated around a diameter like this, and that rotation is at the slower angular speed, capital omega. And it takes one full orbit for it to rotate entirely around. If that rotation weren't happening, this wouldn't make sense physically the way I have it set up. But as an object, if that rotation weren't happening, what that would mean is that this face with the dot on it would always be pointing to the right as the disk moved around. If it had an independent pivot point right at the center, it would be physically possible for it to do that. That's not what's happening in this case. In this case, this face is always pointing outward, radially away from the pivot point, and that results in a rotation around this diameter. Now, it turns out that moment of inertia, which I'll call I2, happens to be half the moment of inertia for this axis. So in this case, it's 1/4
I wonder.
mr squared.
I wonder.
Okay, so that is another kind of rotation that's happening about center of mass. And so there's an additional angular momentum term arising from that rotation, and that's equal to I2 times the angular velocity of that rotation, which is capital omega. And because the axis there is the z-axis, this is pointing in the k hat direction. So the total angular momentum of the gyroscope is I1 times omega in the r hat direction, plus I2 times capital omega in the k hat direction, plus m omega capital omega d squared in the k hat direction. The first term, the r hat component, is the only part that's rotating. So this is a rotating vector. The k hat terms are constant. This is the exact expression for the angular momentum of the gyroscope. And now we see the gyroscopic approximation, more precisely, is saying that this rotating term dominates over the other two terms. So it's actually that this term is very large compared to either of these two terms, which, as we can see, is roughly equivalent to saying that little omega is very large compared to big omega.
Okay, I'm done. Cancel. And
Super pokloni.
nope, we're going here. We're going here. Okay. So, classical mechanics. Because I was not talking. I wasn't talking, I was letting him talk. Do I still not, am I still not hearable? Let me check.
Rotation weren't happening. This wouldn't make sense physically the way I have it set up. But as an object,
Wait, we gotta wait. Do I still not, am I still I'm not hearable. hearable? I'm hearable. I'm hearable. I know I'm hearable. Okay. Baš se slabo čuješ. Jebi ga. Svako smo završili za danas. Anyhow, we did the course, complete course. I'm gonna increase my voice just so we're okay. Now you can hear me. We did the complete course. We did rotations, translations, potential, continuous mass, everything. We did everything. Everything in classical mechanics. Now, that's the syllabus. Online textbook. That was the online textbook. I didn't know we had an online textbook. Maybe I should have used it. Readings, chapters. Okay, assignments. Next time we'll go through the assignments. And then vectors and scalars. Okay. Okay. Okay, where's my stuff? This is syllabus. Yeah. Thank you. Projects, exams. And I can go to an exam right now and see how good would I do on this exam. First we'll practice a bit, then we'll try an exam, grade ourselves, and if we pass, then we can, you know, we download this and save and open. You have 5 problems, 19 minutes. Show all work. Be sure to circle your final answer. Read questions carefully. Okay. Problem 1. Quick multiple choice questions. Okay. For each of the following, you need to ensure any work. Which is not valid force law? Okay. Okay, you just do this. That. A tidal is flat surface of the constant velocity omega. And velocity is shown in the diagram. In which direction does the function roll act on right? Zoom. 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 J hat. A hat. From the road act on the friction does not act on the tire, I think. Okay, you'll be using this massive flat table table brake is sufficient so that the brake remains at rest compared to the force which you would pull in a rope. The unit rope exists the brake is you pull a brake of mass m sitting on a flat table using a thick rope of mass m. Okay, okay. Friction between the superposition table and the brake is sufficient so that the brake remains at rest compared to the force with which you pull one of the end of the rope. The force at the other end of the rope exerts on the brake is same. Oh, fuck. It's a thick rope. It's a thick rope of mass m. So this is the same as doing it like that. So here it's the least, the greatest force, and here is the zero force. It's a less. Next. A swinging pendulum passes through a lowest point. In which direction does the total net force act? A swinging pendulum passes through its lowest point. In which direction total net force act? It's a swinging pendulum. The net force is 0 at the equilibrium point. Yes, the net force is 0 at the equilibrium point. A pendulum with a mass m and length l is releases a small angle of vertical offsets with period p. If they double the mass and half pendulum, the new period is okay. I would have to do some calculations here. Okay, problem accelerated output machine. Oh god. I think I will be able to do this one. Next, the hanging rope. I think I'll be able to do this one. Next, do not slip. I don't know what this is. Okay. Will the agency destroy the world? Speculation. Uh, it might create let's imagine the DLC does create such a black hole as assume initial once it's formed initially creates a black hole will immediately fall under using dimensionalized come up with an order of magnitude search for its relation pass through the earth based on relevant parameters of this problem. Okay. One is assumed the particle collision converts equivalent of an entire year's worth of global energy production into a single black hole at rest. Also, the radius of black hole distance. Okay, this is a black hole problem. Okay, I think I'll be able to do this now that okay. So these are exams. This is exam 1, exam 2, exam. What is the final exam? Final exam? Final exam. Do all 7 problems. You have 2.5 hours. Okay. Alright. Alright. Okay, not too powerful. 2.5 hours is a bit well, but I'll do it. Assignments. I just have to do assignments. To train the RB, I don't think that's a good assignment for what we are doing here. Not neither are these. Okay. Well, that's it, folks. We finished the stream at 12 today. I'm kind of tired, so I'm not gonna do exams. I'm not gonna do that sort of thing right now. I will be doing it the next time we see. I'm gonna go write stuff. I feel like writing. Thank you for coming and listening for these 3 hours. We finished mechanics and we are on our way to finish more. So how many videos did it take? 1, 2, 3, 4. Oh, did I? 5 videos. It took me this is 12 hours. 12 hours. For mechanics, I anticipated 15. Now I anticipate 15 for examples, and maybe I'm off, and it takes me less. Well, we'll see.